So thanks again for having me here. Basically what I tried to put together are about 4 talks, and we can kind of take breaks as people need them, and breaks maybe at the end of each one, short breaks. I think short breaks are nice as opposed to one big long break. So I wanted to kind of talk about some longitudinal analyses. In my emails with Anne, trying to figure out what to talk about, we've talked about growth modeling and growth mixture modeling. She also talked about using R a bit, so I've put some of the R programming into it from more of a multi-level perspective. So basically what I'm going to be covering is some basics of growth modeling, growth mixture modeling, with kind of a multi-level and SEM point of view. The SEM point of view is going to be primarily programmed in Mplus, and I've been told that's what people use here, so that's good. And then the multi-level modeling will come mostly from R and using the package NLME. So that's what we'll start with. And if you have any questions, just please stop me. I can just keep on talking. So just raise your hand, stop me, and I'll do my best to answer those questions. So to begin, I want to kind of talk about things to do before you get to growth modeling, and these are some really important aspects to think about before you kind of jump into growth modeling. And I'll say that I'm kind of at fault with a lot of these things. I want to just get into the analyses, start fitting some models, start trying to understand what's going on in the data without paying careful attention to what the data look like. And of course, it's burned me several times. I remember I was in graduate school, and I had this idea about reading in mathematics, and I pulled down some data from the Nels study, and I started analyzing the data right away. I had my effect going exactly how I wanted, a positive effect from reading to mathematics in these complicated models. And then, then I looked at the descriptives, and they seemed a little off. And it turned out there were 2 missing data codes. They used a period for one, which I accounted for, and then -99 for the other. So that really kind of hurt my analyses. And then, of course, when I corrected that, my effect was gone. So another example, and hopefully if I learned since graduate school, but again, it comes from graduate school, where I was fitting these growth models, and it turned out I had 2 people in the data set that were 1900 years old instead of 19 years old. So, I was talking about that vocabulary ability didn't decline at all as people got older, because there was 2 people 1900 years old at the end, and they looked pretty good. So obviously getting rid of those, things start to decline a little bit. So these are some things that I've kind of, thought a good bit about. The chapters I sent you are from a book that's a work in progress. So if you want more of the book in progress, let me know. I'm happy to send it to people. We're going to talk a little bit about data collection schemes, and here it's kind of, thinking about how you might want to go about collecting longitudinal data, but also thinking about the data that you probably already have collected and different ways to think about it. We'll talk about different ways to organize your longitudinal data in your statistical programs, and again, we're going to focus mostly on R. We'll talk a little bit about making some longitudinal plots, some data screening, and then a bit about longitudinal measurement, which is very different from how people conceptualize, evaluating measurement in cross-sectional studies. So typical longitudinal data is really collected as at least for analyses where you're going to be looking at growth, we often collect data, we call it panel data. You have kind of these fixed time points where people are assessed. These are multidimensional data, so you might be collecting data on various constructs. We have more people than we have observations. So typically the number of observations is relatively few, the number of people is relatively large. And this is our typical kind of sense of longitudinal data. And these data can kind of come about in various ways. So we can have what's called a single cohort study, which is where we collect people at a first time point, that they're all the same essentially at that first time point with respect to the time metric we're looking at. And I'll give you an example of that. There's an unstructured multi-cohort study, which is kind of like a cross-sectional study that becomes a longitudinal study. You're not really planning for it to be a longitudinal study from the outset, but you collect your cross-sectional data, and then you're like, oh, it'd be a really good idea if we get some of those people back. And so then you keep on trying to track these people. And then there's something called the accelerated longitudinal study, which is where you purposely plan to essentially miss people's occasions. Okay? And you do this in a very systematic way so that you can look at change over a longer period of time with shorter amounts of data. And this goes back to work by Dick Bell in 1953 and 1954. And I think the best thing, if you look at his papers on this, you'll notice that the paper that was published in 1953 was actually accepted in 1954. So that's a really nice way to get accelerated in life. So we have a single cohort study, and this is typically what people think about. We have a sample of individuals enrolled at the same time point with respect to the researcher's time scale. So if we're doing a study about schooling, like the early childhood longitudinal study is a perfect example of this. We're interested in schooling. We assess everyone in kindergarten to begin with, and then we follow them at very defined intervals. So maybe we assess people in the fall of kindergarten, the spring of kindergarten, the fall of first grade, the spring of first grade. So we have essentially one cohort of individuals that is moving through our study. So in the ECLSK, we have assessments in kindergarten, first grade, third grade, fifth grade, and eighth grade. If we're trying to, from a data collection standpoint, we're interested in schooling. So we're collecting this cohort related to schooling. So our time metric is really about how school might influence some changes, whether or not these are academic changes or social changes. The spacing of observations doesn't need to be equal, but typically in these studies, people like to be consistent. Just a side note, being inconsistent is often a good thing with data collection. If you're always going to assess people at certain time points, you're going to actually limit yourself in what you can do with it. So actually being inconsistent in when you assess people, and being also inconsistent in when you assess different people. So you might have some people that are assessed maybe twice in kindergarten, twice in first grade, and other people that are assessed maybe 3 times in kindergarten and not at all in first grade. So if you're inconsistent with your measurement, you actually can gain something. All participants are essentially assessed at each one of these measurement occasions. The unstructured multiple cohort study, like I said, it kind of starts out as a cross-sectional study, and then you realize, wow, it would be, maybe you get a new grant, and you're like, wow, it would be a really good idea if we go back and collect more data on those individuals. So we go back in. So at the first time point, where it's just a cross-sectional study, you might have a cross-section of the sample. So maybe we're studying something related to age. So we have cross-sectional differences in age at this first assessment. So then when we assess the people again, they're still very different in their timing of assessments with respect to age. But it's everyone's second assessment. Now there's lots of ways you can think about trying to analyze these data. You can think about using age as the real driving force. If age was the time metric that you thought about, you were interested in age changes or age differences, then using age when you're going into the analyses makes sense. But sometimes what people do is they transition to a kind of an occasion-based study. We'll say, oh, well, this is everyone's first time point, and this is everyone's second time point. So let's just look at change from time 1 to time 2. Okay? Now, that time metric is something that you gave them. Okay? It's not something that they had. It's something that you gave to them. And anytime you're studying change on a time metric that you gave them, you might kind of be missing some of the point, unless you do something to them. If you perform surgery on them, okay? So you do your surgery, and then you see how they recover. That makes sense. If we're just pulling people out of school and giving them a math test and saying time 1, time 2, that math test hopefully didn't have a major impact on their life, okay? So thinking about the time metric that you might analyze these data becomes very important. One of the studies that I use a lot that you'll see today is the National Longitudinal Survey of Youth, Children and Young Adults. The first data collection began in 1986. it was all children of female respondents to an earlier study, or all children of female respondents who responded to an earlier study. So these children were very different ages in 1986. And then 2 years later, they decided to try to assess everyone again. 2 years later, the same thing. So at each time point, it's a real, kind of cross-section of the study. There's even people that were, say, born in 1990 that were then enrolled in the study after the study already began. And some people, were, of course, lost to follow-up. These data actually go from 1986 all the way to 2012. So every 2 years, some of these individuals were assessed. And this study just continues to evolve. Another one is the National Study of Growth and Change. The National Study of Growth and Change started as a standardization sample for the Woodcock-Johnson. So it's a big cross-sectional sample of the United States, from young kids to older adults. And then they decided to follow up these people over time. And so again, you have this big cross-sectional sample that's followed up over a 2-year period. Now again, when you think about the time metric in these studies, with these studies, you probably want to think about that original time metric. If you're interested in age, use age, as opposed to using measurement occasion. Now you might ask yourself, why do people use measurement occasion? It's easier, okay? Models will converge more likely. Using age is more difficult. And then you have to think about how precise you want to think about their age. Is it, the person's 8 years old, 9 years old, 10 years old, or is the person, 762 days old? And if you think about how finely you want to measure age, every time you round, you're losing something. So if you can measure it more precisely, you're going to gain strength in that. The accelerated longitudinal study, like I said, goes back to some papers by Dick Bell in the 1950s. This is a type of study it's a longitudinal study that's planned ahead of time. And the goal in most of these studies is to look at, say, age differences, and maybe a large span of ages. So you might be thinking about studying a developmental process that begins at age 5 and goes to age 15. So it's essentially an 11-year study that you want to carry out. But NIH says you can't submit an 11-year study. You need a 3-year study, and they'll pay you for 5 years. So you think about, how can I get from 5 to age 15 with just 3 years of data? Well, what if we started people at different ages? So we have a sample of 5-year-olds, maybe a sample of 8-year-olds, and a sample of 11-year-olds, and we assess them for a number of years. And if we think about that, these individuals, the 5-year-olds, are essentially the same as the 8-year-olds, which are the same as the 11-year-olds, we might be able to model the changes that take place beginning at age 5 and going all the way to age 14 or 15. Now, of course, there's a lot of theory that goes into this, a lot of assumptions that you're going to make about these individuals, that they are the same over time. Sometimes there might be a big event that makes these people not the same. There's a collection of studies called the intergenerational studies, and one cohort was born in 1920. The other cohort was born in 1928, and they followed these individuals over time. And the big event was the Great Depression. And this Great Depression was found to influence these individuals in different ways. So for the kids that were born in 1928, a lot of times their mothers had to go to work. So they were at home as young kids without their mother at home, which was very different in 1930. The kids that were born in 1919, a lot of them actually had to go to work because their parents couldn't find work. My grandfather was born in 1919, and he was singing in bars when he was a teenager to make money. So that event, really changed how these people, developed. And so there's a lot of interesting papers by Glenn Elder on this phenomenon with respect to the Great Depression. So if we think about all the time points that we could assess somebody, we have ages in this bracket. We have the cohort, or you can think about maybe as year that they were born. This is the year of the assessment, and this is how old they would be. If we were going to do a cross-sectional study, we would be making one collection, so say in 2012, and we would have people that are different with respect to age. So we would think about some age phenomenon, and maybe we would be looking at age differences here, as opposed to age changes. If we're doing a typical longitudinal study, we follow a single cohort. So this cohort was born in 2002, and they're assessed at pretty defined intervals over time. If you think about the accelerated longitudinal study, we really have something like this. So our longitudinal study takes place in a shorter amount of time. Okay, so we're just collecting data in 2010, 2012, and 2014, but our age span goes from 2 all the way to 22. So we can start to think about an age process that is almost goes, from infancy or toddlers all the way to young adults. Okay, with just in this case, it would be a 4-year study. All right, so once we have our longitudinal data collected, we need to think about different ways we can organize the data. And typically there are 2 formats to organize our data. Oftentimes they're referred to as the wide form and the long form. They're also referred to as vector and matrix. They're also referred to as person-centered and person-period. But wide and long is, simple, so I like it. So in the wide form, you have 1 record for each person. So your longitudinal data are essentially stretched out wide. And if you think about this data set, you have as many records as you have people. So your data set is not very tall or long, but you have lots of variables assessed over time. So that's why it's a very wide data set, and that's why it's referred to as wide. If the wide data set is necessary if we're going to be using structural equation modeling programs to fit growth models and growth mixture models. Now, Mplus can also has a multi-level feature. If you're using the multi-level features of Mplus, you need the other data set, or the other form of the data set. But for typical structural equation modeling, you need the wide form of the data set. The other form is the long form, where we have multiple records for each person. So each person appears in your data set multiple times, and each time they appear, it's 1 assessment. So if a person was assessed 5 times, they would have 5 records. There would be a time variable that says when they were assessed, and then you would just have say you have 1 collection of variables, and the longitudinal data are stretched out in a long format. Okay, these data sets, or this type of data set, is how growth models are fit within the multi-level modeling framework. So if you're using proc mixed in SAS or NLME and R, you need the long form of the data set. A lot of the longitudinal plots that you can make requires this type of this structure of the data set as well. So being familiar with these 2 types of data sets and being able to go from one type to the other becomes really important, because you don't want to be stuck in one. You don't want someone to give you one type of data set and I can only do this. You need to be able to go back and forth between the 2 types of data structures. So here's an example of the long data set. So we have this first person was assessed 4 times. This is my time metric, and these are the scores that they had. This second person was assessed 5 times. These are the times that this person was assessed and their scores. Now, one thing about the long form of the data set is it's hard to really understand some things about missing data. Okay? Because you might notice that person number 2 was assessed at age 2, but person number 1 wasn't. Okay, and of course we could add a record for person number 1, say age 2, not there, but that's basically just wasting space in your data file. But this is the form of the data that we need for plotting. If we take this same data and we look at it in a wide form, you start to understand that there are missing data here. Okay, so we have person 1, and now the variables I have are y2 through y7. Okay. So the longitudinal information about when people were assessed is now within the variable names. So this is the y variable measured at time 2, or whatever time is, age, if it's grade 2 or age 2. And now we can see that person 1 is missing, person 2 has a score of 4. At time, say age 5, this person's missing, but then at age 7, this person's missing. So even though this initial data structure and the long form appears complete, if we think about stretching it across the time metric, it's really somewhat incomplete. And since these data structures are essentially inherently incomplete, we need to be able to fit models where we account for missing data. Okay. Now it might be more obvious in the SCM framework when our data look like this and we have holes in our data set, but no matter what your data are, you're going to have missing data. if you think about when people were actually assessed, no two people are assessed exactly at the same time. You know, the closest I've seen it was in the intergenerational studies, where these kids were assessed on their birthdays. And if you actually look at the files, they were almost always assessed within a week of their birthday. It's like, happy birthday, come on in, take some cognitive tests. You know, here's the Stanford Binet, and let me, you know, write these things down about you. And a lot of kids came in on their birthday, you know, but this was, you know, the 1930s. You can't do this anymore. Before IRBs, we're going to force kids to come in on their birthday and take tests. You know, but nobody, and you can think about, again, how finely you want to measure time. You know, time, you know, we often, you know, truncate at some point, but you can measure time extremely fine, and in a sense, nobody would be assessed at the same time point. So the data that I'm going to work with come from the National Longitudinal Survey of Youth, children and young adults. This is a data set that you can pull down from the web. If you're interested in the data set that I have here, I'm happy to send it to you. Since it's public use, I can do whatever I want with it. The participants were children of female respondents from a previous study, the National Longitudinal Survey of Youth in 1979. Data collection began in 1986, continued every 2 years. It's that unstructured longitudinal study. The initial organization of the data is in the long form, okay? And oftentimes it's easier to kind of keep data in the long form initially, okay? And the reason why I say this is because if you think about a time metric, okay, in the long form, the time metric is just a variable, okay? And you can have multiple time metrics. You could have their age, you could have their grade, you could have their measurement occasion. These are all just separate variables. Once you put the data in a wide format, you're imposing a structure of time, because you have to get it into the wide format, the variable name has the timing information in it. So it might be, you know, Y1, which is occasion 1, but people might be different ages. So you're kind of already assuming that you know the time metric. Where if you keep the data in the long format initially, you can have multiple time metrics, and then if someone wants to use, say, structural equation models to fit growth models, they need to think about the time metric first before they transform the data. Okay? So the initial data are in this long format. So here's some R code, and I've heard people are familiar with R, so I'll assume that's the case. I also have code in SAS, and we're working on code for SPSS, so if you do want different programs, just let me know. I can always send things to you. So we're reading this data set in. I'm calling it weight long because I'm really interested in the weight of these individuals. In R, we can just use read.table. So this is, we'll read our data file in. This is the location of the file. I say that I have missing data, and the missing data strings are dots. The next thing I do here is to provide the names of the variables in my data set, because I have no header. Okay, so my data set are just numbers. So I provide names for all the variables in my data set. Now, to begin, I'm going to use age as my time metric. Okay, and age here is measured somewhat precisely. Okay, so we have lots of decimal points. So the first thing I decide to do is to simply round age. Okay, so I'm creating a variable called age underscore R, which is simply the rounded version of age. Now, yeah, no, that'd be perfect. I agree. Almost worked. Almost. No, my hands are getting cold up here. No problem. All right, so I'm rounding age here. Okay. Now it's important to note how age is rounded in R. Right. R rounds things differently than most programs, and I found this out when I did this. So if you have a score that's 1.5, you round up, right? 0.5, you go up to 2, okay? And R will do that with 1.5, but with 2.5, R will go down to 2, okay? So the reason it does this, it's actually kind of smart, but it really threw me off for a while. If you're always rounding things up, you're going to bias the scores. You're going to bias age. You're basically assuming people are older than they really are. So what R does is it rounds to the closest even number. So if it's 1.5, it will round up to 2. but if it's 2.5, it'll round down to 2. So it actually rounds to the closest even number. And again, I only figured this out when I started to look at these descriptives, and then one of my co-authors said, you know, your SAS data look different from your R data. I was like, oh, damn it. All right, so I'm going to round age because I'm going to flip this data to be stretched out wide according to age. And essentially, when you do this, I need to kind of have these, we call them buckets or bins, where I'm going to kind of put people's scores in. So if you're around age 8, I'm going to put you in this age 8 variable, this weight at age 8, okay? And this is one of the limitations of using SEM for doing growth models. But now, you know, with SEM and doing growth models, they can handle individuals that vary in their time metrics. The SEM programs can do this now. It was kind of a competition, of course, between the multi-level modelers and the SEM modelers. You know, they want to say we're better, you know, you guys aren't as good as us. And the multi-level people said, well, we can fit models where everyone is assessed at different time points. And they said, you know, you SEMers can't. And so then, of course, the programs say, well, we can do that too. And then they figure out how to do it. I mean, basically what they do is they turn their program into a multi-level program. So SEM programs can now do this. But for the time being, we're going to use the basic structural equation modeling framework. So I'm rounding age to the nearest year for the most part. And then in R, I'm going to use this reshape command. This will let me go from my long data set to my wide data set. So I say reshape, this is my initial data set. This is the name of the variable that's going to vary with time. So v.names is weight. I have a weight variable that's going to vary with time. My ID variable is my identification variable for each individual. My time variable is my rounded age. And the direction that I want to reshape is to go into the wide format. So this will take my data from the long format and spit it into the wide format, which is great. I mean, it's a very simple set of commands in R. Then the next thing I do is I simply kind of truncate my data because I just want to focus on these weight variables. I don't want all the extra variables. So I simply am selecting these variables. And the way that R names the variables is it gives the weight variable and then dot the age variable. So weight.5, weight.6 are the names of the variables that R creates for this wide data set. Now I don't like these names, so then I simply change them. And so down here, I give new names to these variables. So I have my ID variable and then just weight 5 all the way up to weight 19, just using the names command. So once I have the data in the wide format, I can have my data be ready for structural equation modeling programs. I can look at descriptive statistics, but of course, you might be given the data set in the wide format where you want to go to the long format. So to go backwards, we have to reshape the other way, okay? So we still use this reshape command. The original data set now is the wide form of my data set, so weight wide 1. My ID variable is still my ID variable. The varying variables are all of my weight variables. So these are all the variables that vary with time, okay? The times command tells me when these variables were assessed. So this is essentially it's my age variable. I'm putting it back in, okay? And then I want all of these variables to be contained in this weight new variable. And then the direction I'm going in is this long format, okay? So I take these about 14 weight variables and I put them into a single weight variable with people assessed multiple times appearing in different records of the data set. The last two things I do here is just to kind of clean up the data file a little bit. So if I flip this data set, I'm going to have essentially 14 records for each person, even though they're only assessed about 4 or 5 times. Okay, so I have a lot of missing data. So this command here just gets rid of those missing values. So basically, I'm going to have rows where I'm going to have the ID, the age, but no weight. So that row doesn't give me any additional information. So these last commands just get rid of those rows. So my data set is more manageable. All right. For longitudinal plots, I think these are some of the most important things to do kind of before you jump into fitting growth models, is to plot your data, okay? Now the longitudinal plot that we'll kind of focus on can be really informative. You can look for outliers, you can look for miscodes, you can look for the person that's 1900 years old, because they should appear in this plot. And you know, when I was doing the work in graduate school, I was restricting the age range of my plot, so that person would not appear. So that's why I missed it. But the first time you plot, make sure you plot all the data. So you can look for outliers. You can think about what types of growth models might be reasonable for your data. I don't think there's anything wrong with kind of looking at your data ahead of time. Some people think, you know, I'm cheating. Well, like, you know, you see a linear trend and you fit a linear trend. You're like, well, you saw it first. You know, did you have a theory about a linear trend? Well, you know, I can start with a linear trend, of course, but like, I think you should plot your data to kind of see what might work. You know, you know, if I want to really replicate, you know, I need to go get a new sample, and that's a lot of money. So, like I said, a lot of problems can be avoided by carefully examining your data. Yes?
So, what I've always been told, and then go to your data, because your data has like 8,000 records or 10,000 records. Like,
you don't want to plot
with like 22,000 kindergartners.
Yeah, that's right.
So, I mean, if
you don't want
a random sample, then you miss those 1,900.
You could. You could.
What is your suggestion? Because like 8,000 lines is just
8,000 lines is a big mess. All right. It's good to plot it though. Okay. And then plot a smaller subsample, because that big mess will catch everybody. Okay. And then the smaller subsample will kind of start to track. You can see more about how people are actually changing. So you'll see. All right. So, and you'll see soon, not right now. So here's everyone I selected for this study. Okay, I selected these people in a very specific way that I'll tell you about later. But what I'm using down here is chronological age. Okay, and on the y-axis is simply their weight. So from this plot, you know, we can try to see something about how people are changing, but also try to pull out some people that just have odd observations. You know, and these data are slightly cleaned, but not thoroughly cleaned. Okay, so like I got rid of the people that were like, you know, 8 years old and 5 pounds. Okay, but these data are, you know, they're for the most part they're what I pull down from the web, and with any public use data file, it's going to be messy. You know, they collect data on so many people. There's going to be miscodes. There's going to be people that, you know, gained 100 pounds in a year. You know, these things just are unlikely to happen. But from this plot, we can get a sense of how weight is increasing from age 5 all the way to age 15. Now, based on this plot, if you fit a linear model, if you're trying to fit lines through this, you're going to realize you're not going to capture this data. Okay? You see that for the most part, there's very little increases in weight down here, but then all of a sudden, people really start to expand, and they really start to go off in different directions. So there's an acceleration of the changes with weight with respect to age. So maybe an exponential model might capture these data better than a linear model. To make this type of plot in R, there's lots of different ways you can do it. There's a package called ggplot2, which is a fairly recent package in R that's very good. There's a really good book on longitudinal data analysis by Jeff Long, and it's about doing growth models in R. And he has a whole chapter on plotting, which is just fantastic. And for the most part, what he talks about is using the newer linear mixed effects modeling package in R, which is LME4, which is a very good package for doing linear types of models. So again, here I'm just randomly selecting some individuals for this plot. I'm invoking my ggplot command here. This is my data set. These are some of the aesthetics. My x variable is age, my y variable is weight. I'm grouping people according to ID. These are simply some aspects of the plot that I want to try to control. So essentially what the plot will look like, I want to connect individuals with a line. I want every data point to be represented by a point, and theme classic is about the background of the plot. So this is just a very simple one. And then for my x-axis and y-axis, I have the breaks that I want, the label that I want for both of these, and then I simply print that. So that will give me a plot that's very much like this plot. The background will be slightly different, but it's very much like this plot. Now, some basic data screening. So the thing that I'm really terrible at doing. Look at your univariate plots. I mean, these are boring. You know, who wants to do this? You know, you get your data from your advisor, you just collected all this data, you want to analyze it. Try to do this first. Thanks. So, you know, look at your basic descriptive statistics, mean, medians, variance, standard deviations, skewness, kurtosis, minimums, maximums, ranges, the number of observations, all very important information. And also important information when you're thinking about growth models. If you're calculating the mean, say at each age, you can start to see how the mean changes over time. And if the mean changes in a nonlinear fashion and you're fitting linear models, and then you're wondering why your linear models don't fit, is because the mean doesn't follow a linear trend. Okay, so think about looking at these descriptives, but it's not just, you know, descriptive statistic at one time point. It's descriptive statistics over time. So they actually provide a lot of information. Look at correlations, covariances, bivariate frequencies if you have ordinal data. Look for patterns, nonlinear relations, outliers, miscodes, all of the above. Now these longitudinal data are special. They're special because they're ordered, okay? And now when you get into looking at your descriptive statistics, you have to start thinking about your time metric, okay? Because remember, if your data are in the long form, you have one outcome variable, okay? And you can calculate the descriptive statistics on that one outcome variable, but those descriptive statistics are complicated by the fact that you have the same person in there multiple times. So the best way to look at descriptive statistics is to use the wide data set, okay? So you need to think about your time metric because how you organize your wide data set is according to that time metric. And so if you're going to use, say, age as your time metric, you don't want to look at your descriptive statistics in terms of measurement occasion. You're going to want to look at them with respect to age. Okay? So you need to think about what time metric you're going to use for your analyses when you start to look at descriptive statistics. Now this may be really difficult because, again, people might be assessed at very different time points. And that's why putting people into these bins or these blocks where people are about the same, you know, point in the developmental process. And again, I'm going to use age here. So I'm rounding age so I can start to look at descriptives. Okay, so I'm going to look at these descriptive statistics with respect to age because that's how I'm going to organize this longitudinal data set. The change in the mean can be very important for thinking about different types of models. The change in the variance. When you're fitting, say, a linear growth model, there's a very specific expectation for how the variance will change over time. Now, if you're looking at your longitudinal data and you see that the mean changes linearly with time, but the variance doesn't change in a constant way, then a linear model will not fit your data. You know, especially if you have some periods where the variance really explodes and then the variance comes back down again. You go to fit your linear model and then you have a negative variance and nobody's happy with negative variances. So looking at these means, but also the variances, the covariances, the correlations over time to really understand how the correlation changes over time. All that information goes into the estimation of the growth model. So you need to think about this. If you're one that really likes growth mixture modeling, what you're really hoping for is non-normal data. Now it's really sad to say because we always strive to correct non-normality. You do your transformations, but if you want groups, you need non-normal data. If you have normal data, that's nice and pretty, you will not find any groups, okay? Now with growth mixture models, the way the non-normality changes over time becomes important because you might start with something that's very normal that eventually becomes non-normal. And what that would suggest is that you might have a mixture in the slope, because over time people are kind of clustering to one area. So looking at these things becomes really important to really get your mind thinking about the types of models that you're going to fit. So again, we're dealing with the wide data set here. Here's some basic R code. There's the psych library that you're probably familiar with. There's a describe command within the psych library that provides a lot of the basic univariate information. We can get correlations using the core command. And then the information here is about making it's called a panel histogram diagram, which is really nice. Along the diagonals of this kind of matrix, you have histograms. In the off diagonals, you have scatter plots. Okay? So in terms of this code, this part of the code you just leave all the same, and then this part of the code is where you kind of enter your variable information. And again, we're working with the wide data set here. So here are some basic descriptives. This technically is output from SAS, but we can start to get a sense of these changes in weight. So the first thing to notice is my sample size. Right? My sample size, most of my data are right in here. Okay? So most of my data are collected from about age 7 through about age 13. Now it's important to understand this because that's the data that's going to have the most control over my estimates. Okay? The fact that I have 8 people that are 19 years old, it's really not going to care much about those people. Okay? Even though they're kind of on the end of the x-axis, most of the data, where I'm getting most of my fit information, will come from these individuals right here, because that's where I have most of my data. But if we look at how the mean changes, you see the mean starts by only maybe changing 4 or 5 or 6 pounds, and then once you get to about age 7, we start jumping up by 10 pounds. When you get to about puberty, we start increasing at a faster rate. So about 12 pounds, 13 pounds, and then things start to calm down a little bit. Okay? The other thing to realize with these descriptive statistics is that some of these numbers are more reliable than others. Okay? The numbers that are most reliable, of course, come from where most of our data are. Okay? Sometimes you might see age 19, we have people here that are 130 pounds or something. And you say, oh, all of a sudden people are losing weight from age 18 to 19. No. Okay? First, those people probably weren't assessed at age 18, but there's only a few people there. Okay? So we need to think about these numbers and take into consideration how many people these numbers are based upon. Again, if you look at the mins, I actually have someone who's 1 pound. I guess I've missed that person. Age 12, 1 pound. I hope that's not correct. So you can start to see some of the roughness of this data that needs to be kind of smoothed out.
So you mentioned that the fit isn't going to be affected by the people who are on the end because their end is so small. Are they going to affect your parameter estimates more so than the people in the middle?
More so than the people in the middle.
So it's sort of like regression.
Right, absolutely, because they're an outlier on X. So again, doing some basic data screening, we know we have some people here that are just not real people. They're miscodes or they're fairies. The other thing to look at, again, skew and kurtosis. Most of my kurtosis numbers are pretty decent, and then I have this one, 22. All right, so that's of course probably due to a few people. Okay, so people that need to be cleaned out of this data set ahead of time. And again, I didn't do much cleaning on this. I got rid of people that were 0 pounds, but these are the data as I pull them down, and I think it's important to kind of see that. Now this is that scatter plot matrix. So again, I have histograms along the diagonal here, and then I have bivariate scatter plots in the off diagonals. Now the first thing that we notice that at age 5, we're definitely skewed, we're positively skewed here. We have a few people that are potentially, quite heavy at age 5. Maybe those people are not, again, real individuals in my data set. Things to go check. My distribution seems to move in more or less the right direction. It seems like it's becoming somewhat more normal over time, which is something that we might expect. If we look at the scatter plots, you start to notice something about how the data were collected. So remember, data was essentially collected every 2 years. Okay? So if you were assessed at age 5, it's very unlikely that you were assessed at age 6. And actually nobody was. Okay? So my scatter plot for age 5 and 6 is completely empty. I don't have any individuals there. But if you look at age 5 and 7, now we start to have a pretty strong positive association between the weights at age 5 and the weights at age 7, which of course is something that we would expect. Again, with this being weight, we need to think about people that might have changed in very unusual ways. Someone that might have gained a tremendous amount of weight in 2 years, or someone that might have lost a tremendous amount of weight in 2 years, especially at kind of the younger ages. You know, and you see people like this. Okay? Again, this person probably not real. You know, so this person at age 6 compared to age 8, you know, should be somewhere probably more or less in here, and jumps up to 250 pounds. You know, not likely, okay, for a 2-year period to gain about 100 pounds. Okay, so again, looking at making these scatter plots becomes extremely important for just, you know, trying to figure out who's a real data point and who's not. Because again, I didn't collect these data. You know, I don't know what checks went in when they were entering these data. I don't know if they double entered them. You know, so there's going to be a good bit of messiness coming from these data sets that I'm using because they're public use. But even the data sets that you have, you know, we have undergraduates doing coding. You know, there's all these fun issues. I remember, like when I was in grad school, I had to code a lot of data, and then, you know, my advisor was like, I want you to stop coding data, and, you know, let this other person start coding the data, and I couldn't let go. You know, like you can't let go. You're like, no, I know the data I have is good, like it's clean, it's done right, you know. And then someone else starts entering the data, and then I start looking at it after the fact and having to do a lot of post hoc cleaning. You know, and then it was worse when you become a faculty member, because then you're hiring undergraduates to try to code the data that you were doing, and again, you know it so well, and you just expect them to kind of know it so well, but they don't because they just got there, and you know, trying to figure out good ways to clean data is actually really difficult. Besides like looking at your data, you know, doing descriptors like this is a great first step. You know, but to a certain extent, you have to kind of look at your data. I tried to write some programs that would kind of flag individuals that seemed a little unusual, and you can do that. You can simply write code that will flag people that, you know, from a 2-year period gained more than 60 pounds. You know, and it doesn't mean it's a incorrect entry. It just means, you know, maybe go check this person. Okay, so there's things that you can do to just kind of help you clean those data to make sure that you're analyzing the most appropriate data set that you have. All right, so the last topic of the first part is about measurement. And have people in here had measurement classes, psychometrics? Handful. All right. So with cross-sectional measurement, which is what psychometrics really focuses on, you know, you're taught things like, you know, you should have high reliability, you know, you should check for validity, you know, but the nice thing about reliability is there are certain standards, but those standards have kind of led people astray. And I say that because almost the only goal right now when you're developing a survey is to have good reliability and for it to be very short. Okay? Those two things generally don't go well together. Okay? When they go well together, it means you ask the same question 5 times. And you're not actually measuring the construct, you're measuring the question. And so, you know, people, like when people are trying to create a short form, you know, they're getting rid of the items that are hurting their reliability. You know, so you get rid of the items that correlate less. But what it does is it makes your measurement very narrow. So you're not really measuring something that can replicate, you're measuring a question. And there's different ways to go about selecting items. One that I've been talking a little bit about is more of a data mining approach. Say you have all these items, and you're trying to you're trying to figure out which items that give you the most information. So you pick an item that separates the group the most. And then for each one of those groups, you select the item that separates those groups the most. Okay? When you do this, you realize you're going to have items that don't correlate well. Because items that correlate well will not get used in a second step, because all that information went into the first step. So this approach is very different. You're not going to have a highly reliable test if it's short. You'll have a highly reliable test if it's longer. But in terms of measurement, with longitudinal measurement, it's even worse. Because generally what people do is they say, well, I have these good measures that can tell me about between-person differences. Now I'm going to give this to my longitudinal sample. And you have no idea whether or not these measures can actually measure how someone changes. And that's very different from trying to measure between-person differences, whether or not you can measure how someone changes. And I've seen this the most with some of the early kind of preschool work that I've helped with. You know, they're assessing kids over a 6-month period, time 1, time 2, maybe they followed into the next year, and they're giving, for academic achievement, they're giving the Woodcock-Johnson. Now the Woodcock-Johnson was developed to tell us about differences between kids that were as young as 3 and as old as 93, okay? With about, you know, on some tests there's maybe 50 items, maybe 60 items, okay? If we're looking at change over a 6-month period, one item might be all the change that you can expect. Now, if you're measuring change with one item, you're not doing a very good job of it. You know, you really need to think about trying to get items that are focused on the kids' abilities. And there's some work that was done at UPenn where they were trying to do this, where they weren't using the Woodcock-Johnson, they were using tests that they were creating that they were trying to target to this age group. So you could actually see how kids are changing. And so a lot of times, like when I was doing work with Bob Pianta, we were working on this one paper, and you know, we had this measure of preschool quality that you're probably all familiar with. And preschool quality was highly related to academic achievement at the fall of the school year, okay? Because, you know, parents that are somewhat better well off, they are able to get their kids into better preschools, where there are other kids that are, you know, also doing well. So there's a strong correlation between preschool quality and how kids were doing at the initial time point. Now, if you were looking at change from over a 6-month period, there was a strong negative correlation between preschool quality and change in academic achievement. And the reason for this was mostly a measurement problem. Again, we were using the Woodcock-Johnson, and on the Woodcock-Johnson, if you go from a score, essentially a score of one correct item, to 2 correct items, especially on the applied problems test, your W score increases about 30 points. Okay? If you go from getting 5 questions right to 6 questions right, your W score increases 5 points. Okay? Now, part of the reason for this is kids that get 1 question right or 2 questions right, we really don't know anything about them. We have no clue how smart they are, because our test is not made for that kid. Okay? So we're basically taking like a shot in the dark about where that kid's score is. And the way that they come up with these W scores is that they're Roche-based scores, and Roche-based scores always stretch out the extremes. That's where we know the least amount of people, that's where we get the most amount of changes, the most amount of differences. So we had this, you know, strong negative correlation. When we tried to publish it, you know, the editor actually said, your results are contrary to what is known, and I will reject your paper for it. And I was like, but Bob's an author on my paper. Like, Bob's okay with this. You know? No matter. You know, so just because you have a good measure that looks at between-person differences, it doesn't mean it's a good measure to look at change. And that's something that's, you know, there's not a good way to really figure this out, except to try to do it. But really to think about whether or not you could measure change over the time period that you're looking at. So like I said, we typically use the same measurement instrument across time. Do we need to do this? No, you don't. You don't need to give the same test across time. So don't believe anyone that says you must do this. Okay? I know lots of studies do it. the NLSY continues to use the P at R, from 1986, or it might be the original P at for mathematics. You don't need to give the same test. You should be trying to assess the same construct, but you can modify your test over time to try to map on to your participants, to try to target your participants. Just like, with that Woodcott-Johnson applied problems, I think, has like 60 items. For those youngest kids, I'm giving 2 or 3 items. So all those other items are basically a waste of time for those kids. Okay? What would be better is if I have a test that's able to target those kids, to be able to tell differences at that lower end, and then to track my change with the test. Now, if I was assessing people with this applied problems in preschool and 4th grade, I probably wouldn't give the same items at all, because all these cognitive tests, they have a starting rule and a stopping rule. The preschool kid's not going to get to the 4th grade items. The 4th grader is not going to begin with the preschool items. So essentially their tests are different. But the reason why you can still use it is that you already know the information about the test, because that's what Woodcott-Johnson gave you. Okay? They gave you the information about the test. If you get these items correct, this is your score. Okay? We assume you got everything else correct before that. We assume you got everything else wrong after we stop the test. But we're making those assumptions, and that's fine. Okay? But if you're coming up with a scale, there's no reason for you not to do the same thing. Now, there might be some challenges to this. You need to have the information. And where can you get that information from? Cross-sectional sample. Okay? You don't have to give it to your longitudinal sample. Your longitudinal sample is special. These are the people that keep coming back for your study. A cross-sectional sample, you can get once, get the information that you need from them, and then not worry about them coming back. Not worry about overburdening them with more tests. So think about measurement and how you can, again, try to target the people that you're really measuring with your measurement. Other issues are whether or not the assessment, if you're always giving the same assessment, whether or not it is assessing the same construct over time. So this is about looking for measurement invariance over time. Of course, there are items or potentially entire tests that aren't measuring the same thing over time. Some of the good examples come from the child behavior checklist. There's kind of different forms of the child behavior checklist, so they somewhat account for this. But there's a question about like crying. If your 2-year-old cries, all right, 2-year-olds cry. Okay, that's just a fact of life. Okay, now that crying item is not part of the internalizing scale. It's a behavior problem, but it's not part of an internalizing scale in the early form of the CBCL. If you have a 12-year-old that cries a lot, now all of a sudden that item is part of the internalizing scale. Because a 12-year-old that cries is different from a 2-year-old that cries. It's the same thing with like biting. Okay, like my son, he was a biter. It's terrible. Absolutely terrible. But he bit kids. It's like there's nothing you can do. You can try things, but nothing really works. They just grow out of it eventually. So like a 3-year-old that bites, problem behavior for sure. 12-year-old that bites, major problem behavior. Okay? So even though it's the same exact item, it might not mean the same thing over time. Sometimes people talk about like math tests. If you give a very easy math test to a 12th grader, they're just going to try to do it as fast as they can. So it's more about speed. And they're going to make mistakes. If you give that test to a 4th grader, they're going to take their time, and they might actually do better than the 12th grader because the 12th grader was just going fast. So kind of the construct that was being measured changes over time, and that's an important issue. So typically, like I said, we would look at Cronbach's alpha. I'm not going to tell you not to do this, but again, with a lot of the data sets I work with, not everyone has all the items. like the Piat test that I'm going to work with in the next session, there's like 160 items. So nobody took the whole test. So if I'm going to calculate reliability in the typical way of doing Cronbach's alpha, I have to assume either all the items that, you got, all the items before you started the test are correct, all the items after you stop the test are incorrect, just to kind of fill out my data matrix so I can calculate Cronbach's alpha. But you should look at reliability. A lot of times people will report test-retest reliability in longitudinal studies. Don't do this. Test-retest reliability is not reliability in a longitudinal study. It's stability. It's not reliability. And if you're familiar with the work on never use a change score ever, never calculate a difference between two scores and use that as an outcome, that was mostly based on test-retest reliability. Okay? Test-retest reliability is about stability of between-person differences. It's not about reliability. Okay? Reliability is also often based on these between-person correlations. If you're pulling reliability from a scale, between-person associations, applying it to within-person changes is a problem. Okay? Change is always going to be measured less reliably than between-person differences. That's just a fact. Okay? You need one time point to get an estimate of between-person differences. You need two to get an estimate of change. Okay? Two faulty measures will not provide much good information about change. Can it provide good information about change? Yes, but it's not going to provide great information about change. That's why oftentimes people say you should try to get more and more data. But I mean, who wouldn't say get more and more data? Typically with longitudinal studies, we're looking at some sort of raw outcome, whether it's a sum score, an average score. We're not standardizing our data ahead of time, okay? So a sum score is typically what we might use. We just add up all the items, how many did you get correct? A W score comes from, again, the Woodcock-Johnson, which is an estimate of a theta score. If you've taken IRT, a theta is just an ability score, okay? Don't standardize your variables ahead of time. The biggest one that I've seen people use is IQ. So IQ is already standardized for you. It's standardized typically according to age or maybe according to grade. That takes out all the information about change, okay? Because your IQ should stay the same.
If you have something like, let's say you're studying an aging population, you have, let's say a cognition measure. If you combine all your time points and just standardize across
that's fine. You can do that. I'm not sure why you do it, but you could do it.
Well, let's say you had 3 things that you're combining.
Oh, you want to combine things. Factor models. Right. Factor models are great for those things. Factor score estimates, I have no problem with. Again, they're in their own kind of metric. You can, if you apply a standardization, you have to apply the same standardization to everybody. So there's one paper that I worked on where I was dealing with 2 different outcomes. One was depression, one was achievement. They were on drastically different scales. And because they're on drastically different scales, the estimates that I got from them were, completely, you could not compare them. And it's really frustrating, of course, when you are trying to write a paper and the estimate that you get out of Mplus is 0.000. The standard error is 0.000. The t-value is 12, and the significance is 0.000. And you're like, I know it's positive, but it's just in a metric that you can't convey meaning to. Or someone would say, why would I care about that? Well, I can get a standardized one, but there are some models where I actually can't get a standardized estimate of it. And so what I did was I standardized everything based on the time 1 scores. So I found the time 1 mean standard deviation, and I applied that transformation to all the data points. So it retains the changes in the mean, it retains the changes in the variance, as long as you're not standardizing within each time point separately. Yeah, which is essentially what IQ does. it's standardizing within each age. So the raw scores, or these question.
Considering your previous comment that you don't have to use the same measurement at each time point, that the
Mm-hmm.
measurements can change, how would you compare raw scores across your
Sure. So you need information about those scores ahead of time. So whether or not that information comes from a cross-sectional study. So for example, if you have say 2 different IQ measures, or say even if we're working, say you have an applied problems and like the key math, and the key math is a little bit more intensive. But applied problems is just kind of pervasive in terms of how often it's used. If you have a mapping of scores from the applied problems to the key math, you can then apply that mapping. And this, I've often done it with item response models because they're just very useful for doing these exact things. So one study that these intergenerational studies, these studies began in 1928. They are still going on. The last assessment was in 2010. So these kids started out, when they started taking IQ tests, they started out with the Stanford-Binet, Form L, Form M. Then they moved on to the Wechsler-Bellevue. Then they moved on to the Stanford-Binet Form LM. Then they moved on to the WAIS-R, and then the Woodcott-Johnson. And what we were working on is we were taking all the vocabulary tests from those scores and trying to come up with, what a vocabulary score on the WAIS would look like a vocabulary score on the WAIS-R. And so we basically had to create this mapping. And we were able to do this because some of the longitudinal studies actually took both tests at the same time. So they took the Stanford-Binet and they took the WAIS at the same time. So we were able to do this mapping. And we did this with item response models, which allowed us to really map the WAIS and the WAIS-R. So like the vocabulary test from the WAIS-R is not entirely new. It's shorter. It has about 70% of the same items and then 30% new items. And so by using an item response model, we're able to account for the fact that we have some of the same items were administered. Some items were new, but some of the same items were administered. And so we're able to get an estimate of what their underlying ability would be, regardless of what test they took, as long as we had the information. So if you have the information, you can do this. If you just have, if you have no information, you give one test here and one test there, the best you can do is simply predict forward. You can't really look at within person change. But if you have this mapping, you can do it. Other questions about? Okay. So we're using some sort of raw score. Of course, we can transform scores. But again, if you're applying a transformation, apply it to all your scores, the same transformation. Because again, you don't want to transform one of your scores and then have it not be comparable to an untransformed score. So the sensitivity of measurement is more or less what I kind of tried to focus on initially, trying to have an assessment that's sensitive to within-person change over the time period that you're thinking about. Many of these measurements are designed for between-person differences, and they're terrible at measuring change. And a lot of the things that that I have concerns with are a lot of these kind of like behavior rating scales. Because if you think about the person who's rating the behavior, they might be, intuitively kind of accounting for the fact of how old the child is. Like if you gave me the CBCL with my 2-year-old, I would say he's got some problems. If you give it to me now, I'm going to say he's got some problems. Problems different, sure, but he still has some problems. Now, if I were to look at change, you might not see any change, but compared to a 2-year-old, he behaves much better. But the score is not reflecting that. And so with these rating scales, it's really hard to get people to think how you want to get them to think to assess change. And I don't know an answer for doing this. I know some people had tried to talk, had talked about saying, well, like, compared to when we asked you last time, and it's like, well, does the person really remember, when you asked them last time? It wasn't like this significant day. Oh, the day I went into the child study lab and filled out these questionnaires. But you're trying to understand change, and the measurement scale has to kind of be meaningful, has to be able to measure how kids actually have changed. And that's just a very challenging issue. Again, the idea of measurement invariance is that the test is measuring the same construct in the same metric over time. You can assess measurement invariance with factor models. You can assess measurement invariance with item response models. In item response theory, they call it differential item functioning. It's exactly the same thing, except that you don't want differential item functioning. You do want measurement invariance. Okay, so they're essentially exact opposites. In a longitudinal study, you can assess measurement invariance, but again, it can be really challenging, because if you're assessing measurement invariance, you're stretching your data in a wide format. Each time point needs to have its own variables. Okay, so say we wanted to do this at the item level, and we have the applied problems test. We have 60 items at the first time point, 60 items at the second time point, and I have like 200 people. So I have 120 items, a two-factor model, and 200 people. That's just not going to fly. It's just not going to work. So these longitudinal studies can be really underpowered for looking at measurement variance. I'm not saying don't do it, but just be aware that it's going to be underpowered, and you're not going to be able to get everything that you want to get out of it. But you should still at least think about these ideas. You can look for measurement variance in a cross-sectional study. So say we have a longitudinal study with 2-year-olds and 4-year-olds. I might get a cross-sectional sample of 2-year-olds, a cross-sectional sample of 4-year-olds to look at measurement variance. Maybe that will be a little bit more powered, which would be a move in the right direction. It still can't tell us exactly the effect of giving someone the test again, because giving the person the test can kind of change their behavior. If people are familiar with the WAIS, so we were giving the WAIS to a group of older adults over time, and older adults typically don't do well on block design, where these 9 blocks and you have to arrange them in different patterns. So we would take the blocks out, and then the person would say, "I'm not doing that," and you put the blocks back. Okay, so their behavior, their previous experience changed how they, kind of reacted. There was a really, my advisor does a lot of work on cognitive aging, and he said, well, the best way to have people improve scores is to give them the test. Because what you see is with the older adults, if they had the test before, they're doing better. If they have the test the first time, they're not doing so well, because they go home and study. They remember a question. They say, oh, I didn't know that one. I need to find out what the answer to that was. And so that changes their behavior, which can influence measurement invariance. There's a really, if you look at the Stanford-Binet, so the 1937 version of the Stanford-Binet, there's on the vocabulary test, there's 45 items. The 44th item, which is supposed to be the second hardest item, is retroactive. Okay, which to me seems like a fairly easy word compared to some of the other words that were on this test. If you looked at the 1969 version of this, retroactive was still on the test, and it was about like the 18th item. So from 1937 to 1969, the word retroactive became popular. Okay, and people started knowing what it was. So early on, it was hard. Later on, because of changes in the society, probably, that item was now easier. Okay, even though it's the exact same item. Okay, so you need to think about how these items and their information might be changing across time. We've talked about time metrics, which again I think is one of the most important things when you're starting to dive into growth models. Is what is the best time metric? Theoretically, what do you think is really kind of starting to drive these within-person changes? You can always use measurement occasion. Those are easy. Using things that vary at the individual level becomes a little bit more difficult. The other issue is that a lot of time metrics are highly correlated. If you were to look at age and grade, these things are going to be highly correlated. You get older, you typically move up, if you're studying children. Measurement occasion and age, if we could separate those two, that might be a good thing. And that's where I started talking about being inconsistent in your assessment might actually be a powerful thing. Now, I like to ask, what is the correct time metric? I have no idea, okay? You're trying to use something that you think is a proxy for the best time metric, okay? And I've thought a little bit about different ways we can organize these weight data. And the fact that it's weight already kind of ruins my trick. But this is the same individuals. We have, again, their weight on the y-axis, and this is their measurement occasion. So this is the first time that they were there. This is the second time they were there, the third time they were there, the fourth time, and some people came back for a fifth time. Now, I say this is their individual measurement occasion because this measurement occasion is based on when the person showed up, okay? So if the person showed up in 1986, that's 1. If they didn't show up in 1988, but showed up in 1990, that's 2, okay? Because it's based on the person, okay? Now, this might be a reasonable time metric if we're thinking about exposure, okay? Practice effects, exposure effects. How many times did I see you before, okay? But this might be an appropriate time measure. And if I gave you these data and you didn't know this was weight, you would say, all right, sweet, linear growth model, all done. It can make life easy, right? This is the same data based on the study measurement occasion. So the first time you were there, that's 1. If you didn't come back in 2 years, then you have a missing data point at time 2, and you came back 2 years later, that's now your 3. So it's still based on when you started, but it's somewhat tracking the amount of time that took place between your assessments, because each one is approximately 2 years. And again, these data, they look fine. There's nothing obvious that I would say, oh, don't use this time metric. This is a terrible time metric. From a theoretical point of view, I say it's terrible. But from a statistical point of view, I can't really say anything. I like this one. All right, so this is year. And you might think about what things change according to year. Cohort. There might be society changes, and that might impact what's going on in your life. Again, a terrible thing for weight, but these people began in 1986, these people began in 1990, and you kind of see that every few years, people start, and then they keep on increasing. I could fit a model that fits that data pretty well. I wouldn't want to with these data, but again, there's nothing here that really says anything about whether or not I should use this time metric. Here's weight against the amount of time they spent in the study. So now I'm starting to get onto a time metric that's individual. Okay, so I know the dates that you came into the study. I can calculate how many days it's been since you started the study. Okay, and this might be an important time metric. Again, if we do something to you, if we perform surgery, or if I break your leg, you're gonna remember that. I'm gonna see how well you recover from that broken leg. Okay, so this might be an important time metric if this 0 time point is the same thing for everybody. Here's weight against grade. Now it starts to look maybe more of what we expect. Kids are pretty similar in weight when they're younger, and it kind of expands. 0 is, of course, kindergarten. So this starts to get me closer to what I think might be a reasonable time metric. The tough thing about grade, though, is you see people like this. You know what happened? Left back. All right. So you can have, time can pass and you can still be in the same grade. All right. And so that's an issue with grade. I mean, it's just an issue. You can also have like this. This person was really smart. It looks like a lot of time passed, but it's only 2 years. And the person jumped ahead a grade. This is against age that you saw. And again, age is pretty finely measured. we see, an expansion. This preserves the time lag between assessments. The time lag is the amount of time that has passed between the assessments. This will preserve that, just like time and study. Okay, so that's a good thing. And the last one here is gynecological age. So these are all females. Okay, so I selected females from this study, and this is their age at menarche. So that's my new 0 point. Okay, and this might be another way that I can organize my data. If I think how weight changes is really influenced by that time that you go through puberty, then I should organize my data according to that. Okay, so this obviously is going to be highly related to age, but it's not going to be the same. And I'm going to get different information using this time metric than using age. And then other things that we could do, or other issues that might come up, is that oftentimes there's multiple time processes going on. So age might be an important one, grade might be an important one, when you're going to go through puberty might be an important one. So there might be different time metrics that are all ongoing at the same time. And really what we need to do is kind of choose the one that we think is best, unless we can design a study ahead of time. Okay? If we can design a study ahead of time, we might be able to separate these two time metrics. And that's been done a couple times, where in one case they were trying to separate age and retest effects. So what they did is they had people that were different ages at the first time point, and instead of assessing everyone 1 year later, they randomly assigned how long it took you, or how long before they followed you up. And it was as small as 6 months, and it was as large as 2.5 years. So again, being inconsistent in your measurement can be helpful. Another study was trying to look at differences between grade and age. So what they did is they selected kids. So in all schools there's a cutoff. You have to be 5 by August 30th to go to kindergarten. So what they did is they selected kids that were born like August 15th to August 30th, and kids that were born September 1st to September 15th. Now they're almost the exact same age, but they're going to be a year apart in grade. So now you can start to separate age effects from grade effects. Okay? And the researcher that was doing this, he had some pretty clear notions about what outcomes are going to be influenced by grade and what outcomes are just going to be influenced by age. So you can start to separate out these highly correlated time metrics as long as you're in control of when people are assessed. So this is a little bit about those studies designs. Some of the last things you need to think about before jumping into growth models is how you think things are changing. You should go in with some theory. I see typically that people go in with a linear growth model, and that's not a bad thing. It's always a good starting point, and that's what we're going to talk about next. But you should have some notions about what you expect in terms of the change process. You shouldn't just always start with a linear model. You should start with a model that you think is reasonable for that change process. The other thing you need to think about are these between-person differences in the change function. So you might think about, okay, I have a linear growth model. Okay, so a linear growth model, I have an intercept and I have a slope. And typically what people do is they allow for people to vary in their intercept, and they allow people to vary in their slope. And that's just typical. Okay? But there might be certain situations where there might be a parameter that you don't think will actually vary over individuals. It's a parameter of the curve, but you don't think it's going to vary over individuals. So we were doing some work on looking at changes in Tanner stages. So Tanner stage is a metric of pubertal development. Everyone starts at 1 and goes to 5. Okay? And we were fitting logistic models because we thought it was a kind of a smooth change process. It's kind of an S-shaped curve. The logistic model has 5 parameters. It has a lower asymptote, an upper asymptote, a timing parameter, which says when you're accelerating fastest, and then a rate parameter that says how fast you're going. Since everyone started at 1 and ended at 5, the lower and upper asymptote shouldn't vary over individuals. Where we wanted to understand how people differed was in their timing and in their rate, not where they began and where they ended, because by definition, they were going to begin and end at the same point. Similarly, I was doing some work with mathematics, and we were fitting a similar type of curve. And again, the lower asymptote is your predicted value at negative infinity. Okay? And I was looking at changes in math scores. Okay? So what was your math score when you were negative infinity years old? I don't know. Okay? But I'm pretty sure you didn't differ from me in it. Okay? We probably had the same value. You know, now some people got confused because they said, well, people are different when they get to kindergarten. And I said, yeah, they are different when they get to kindergarten, but not, you know, at t equals negative infinity, or for you it's that way. Okay? So there might be certain aspects of the curve that you don't actually think will vary over individuals. And we need to think about that with in-person change process. If there are other time-varying covariates, a time-varying covariate is simply a variable that varies with time. Okay? Time, or age, is a time-varying covariate. But of course, there's other things that go along with that. There might be, you know, changes in relationship. There might be changes in your friends. And if you're tracking change while these other changes are taking place, we need to think about different ways that we might be able to incorporate that into the change process. If we think that event is going to impact your change process, we need to take that into consideration. So it's not just what the function is, but it's all these other aspects of things that are changing that need to kind of go in together. We talked about the between-person differences, and that's what I have for the first talk. Questions? Okay, why don't we take maybe a 5 or 10 minute break, and then we'll move on to the next one.
Okay, great.
Thanks, everyone.
Hi.
To get into growth modeling and some of the issues about fitting these models. So we're going to review some of the basic growth models, which are all going to be linear models. We'll talk a little bit about how these models can be specified within the multi-level modeling framework. We'll talk about the structural equation modeling framework, and then we'll get a little bit into programming, and again using NLME and R, and using Mplus for the structural equation modeling aspects, and then finish with some important considerations. So we're going to begin with a linear model, and if you have interests in models that are not linear, please let me know, because I can send you chapters on them. But to kind of begin with an introduction, we're gonna stick with linear models. So we're going to stick with linear models because essentially they're simple. People typically only fit linear models, which is somewhat of a shame. But the other nice thing about a linear model is it provides you information, assuming it fits, it provides you information that you really want. Okay? There's a slope in a linear model that tells you how people are changing, or how this person is changing over time. And typically when we're fitting growth models, we have questions about how people are changing over time. So it's really nice that there's a parameter in this model that tells us how you're changing over time. So we're going to start with data from the National Longitudinal Survey of Youth, again the children and young adults. The outcome measure is going to be the Peabody Individual Achievement Test, the mathematics scores from them. And again, children were measured beginning in 1986. And I chose a subsample, but this is everybody in my sample. Okay, so like I said, I like to start with this plot because it gives me everybody. Okay, and if we plot everybody, we kind of can see some general shape. You know, so it seems like, you know, thankfully people's scores are increasing. What I'm using down here is my time metric is going to be grade, and part of the reason I'm using grade is because, again, I'm starting, you know, simple. It's a discrete time metric, so it's easy to kind of put people in different grades. Again, it's not a perfect time metric, but I think it's obviously related to changes in mathematics, because I think math will change according to what grade you're in. So we can see that kids' scores are increasing over time, but again, I can't really see individual changes. I just kind of see group level change with this plot. But like I said, people are going to vary in the number of assessments. They were not measured at every grade. They were assessed every 2 years. So approximately it should be every 2 years, or there should be a grade in between. But again, if you think about how assessment can take place, there might be 2 years that have passed, but it might be 3 school years. Or it might be 2 years that have passed, but it might only be 1 school year. If you think about being assessed in the fall of 1 year, you go to the next year and you get assessed in the spring of the following year, it's close to 2 years, but it's only 1 grade. So we need to think about that. But we see positive growth, but it's difficult to see those individual trajectories. And so what I did here is I pulled out a 5% random sample. So this is just one random sample, and I can do this repeatedly. So I can pull out multiple random samples to try to understand more about how people are actually changing. The other thing that's really nice about this plot is I can see more about incomplete data. Okay, I see that this person was just assessed 2 times. Okay, grades 2 and grade 5. Where there's other people that changed more time points. And by looking at these individual trajectories, I might be able to understand more about how individuals are changing as opposed to how the group is changing. And that's a really important difference, because we could have a situation I can do this, right? Where we have a person, say, goes up and goes over. And then we have another person who maybe starts out around the same spot, ends up in the same spot, but gets there in a very different way. Okay? So if we were just looking at a bunch of people that changed somewhat like this, we would say, oh, people increase. Okay? But these 2 ways of increasing are very different. Okay? Now, if this was a math score, I'd rather be this guy than this person. Okay? Maybe this person struggled for a little bit before they figured out, how to do that multiplication. So even though they might be changing in different ways, if we plot everyone, we don't really see those individual differences in how they're changing, which become really important. I mean, this is really why you collected longitudinal data. If you just cared about age differences, you wouldn't care about how they got there. But if you care about how the person changes, this is why you spend the money and the time to do longitudinal research. So we start to see more variability in these changes over time. We see that people differ in the rates of change. They can also potentially differ in the amount of noise in their system. Okay, some people might be very variable. They might be kind of bouncing around all over the place, and some people might be very consistent. You see this sometimes with reaction time data. If you look at reaction time data, some people are paying attention to the exact time, and their trajectory is very smooth. And then you have somebody that's going along, forgets, high reaction time, forgets again. And so the amount of noise in their system varies. And that becomes very important. So essentially, some children might follow a very smooth trajectory, while some kids might be bouncing around a good bit. If you were to look at behavior problems data and differences between boys and girls, you would see that girls are more consistently rated, young girls, than boys. Boys, have these, they just go off on tangents. At least my son does. Where one day he'll be great and the next day he's crazy. The next day he's great and he's crazy. Where my daughter is more consistent. She's a little crazy every day. You start to see some issues of between child variability. People differ in their scores at each time point, but they also differ potentially in the rates of growth. And like I talked, the shape of growth. The shape of growth can become really important. So again, we're going to start with a linear model, and we're going to talk about this linear model within both the multi-level and the structural equation modeling perspectives. So there's 2 models I'm going to talk about that I'm calling linear growth models. One is what people call the linear growth model. The other one is what we call the no growth model, or the intercept only model. The no growth model I always think is a logical starting point. Anytime you're going to study change, it's logical to kind of start with the idea that people aren't changing. Okay? So typically this model I actually want to reject. I don't want this model to fit my data. If this model fits my data, it says people don't change. Which kind of says, why'd you do a longitudinal study? People don't change, and it's like, oh, okay, now I know not to do a longitudinal study for this variable. There's going to be one latent variable. So if we're thinking about the structural equation modeling perspective, there's one latent variable in the intercept-only model because it's just the intercept. From the multi-level point of view, there's one random coefficient. Random coefficient and latent variable I'm going to use interchangeably. One just comes from one framework, the other comes from the other framework. There's going to be this intercept, which is going to be the predicted value over the entire observation period. The other model is what people call the linear growth model. So in the linear growth model, it's very similar to taking each person's data separately and fitting a linear regression to their data. Okay, so if I have 5 time points for the first person, I take those 5 time points, I fit a linear model to it, and from that linear model I have an intercept for that person and I have a slope for that person. Okay, if I do that for everyone, I have a distribution of intercepts and I have a distribution of slopes. So from those distributions I can calculate means, variances, and their covariance. The linear growth model is very much the same thing, okay? But instead of estimating an intercept and slope for each person, I'm just going to estimate the parameters of the intercept and slope. I'm going to estimate its mean, its variance, and their covariance. The last parameter that I'm going to estimate is about the amount of noise that's left over. So there's going to be 2 latent variables. There's going to be an intercept, which is the predicted value at a specific point in time. So we need to think about when that time is going to be. It should be a time point that we care about. And there's going to be a linear slope, which is the predicted rate of change over the entire observation period. Now, one limitation of the linear growth model that you should think about is whether or not this model makes sense for people outside your age range or outside the time metric that you're dealing with. Okay? Linear models sometimes fit well. But if you were to collect the data over a very long time period, the linear model wouldn't fit well. Because life is not linear. Life is nonlinear. Okay? So this model is appropriate starting point, but I hope this is not your end point. Okay? Because life is more complicated. Alright, so we'll begin with the multi-level modeling framework. So the linear growth model is a multi-level model, or a mixed effects model, or a random coefficient model, or a hierarchical linear model. It's all of the above, okay? There's going to be, it's multi-level in the sense that our repeated scores are nested within individuals. So the scores for a given person are likely to be more correlated than scores from different people. We're trying to understand 2 sources of variability. Variability within the person over time, and variability between people, okay? So if you think about multi-level models with kids nested within schools, we're trying to understand variability within the school and variability between schools. With longitudinal data, we're trying to understand variability within an individual over time and between person variability. So for our intercept-only model, we can write it like this, and this is the level 1 equation where we have our observation, y, assessed at time t for individual n, is a function of b1n, which is going to be my random intercept, or my latent variable, which is going to vary over individuals, plus some uniqueness, or sometimes people like to call it a residual or an error term. The error term depends on time and the person. The random coefficient just depends on the person. Okay, so that's why it just has a subscript n. So B1n is the random intercept, UTN is the time-specific residual score. The time-specific residual scores are typically assumed to be normally distributed with a mean of 0 and a constant variance. Now this constant variance really comes from these multi-level models. That's how multi-level models are typically specified, that there's a constant variance across individuals, across time. Now, if you're fitting a model and that residual variance is not constant, and you're assuming that it is, it's actually going to bias parameters. It's not going to bias your mean parameters or your fixed effect parameters. It's going to bias your variance and covariance parameters. The structural equation modeling framework, it's a little bit easier to allow that residual to vary over individual, or over time at least. But there's some really nice work by Don Hedeker. It's called the scale location model, where he allows this unique variance to vary over individuals and over time. And so if you have data where people differ in how much uniqueness they have around a trajectory, you might want to look towards some of Don Hedeker's work. At level 2, we're going to have our random intercept, which is B1n. We have it equal to beta 1, which is going to be my fixed effect parameter, plus D1n, which is essentially a deviation from the fixed effect, or a deviation from the mean. Essentially all we're doing here is we're taking a variable and we're saying it's a function of its mean plus how far away you are from the mean. How far away you are from the mean is going to be distributed normally with a mean of 0 and a variance. Now this variance is a between person variance, okay, because this is a level 2 model. And when I'm writing these multi-level equations, what I'm trying to do is I'm trying to be smart about my notation. Now it's a fight between trying to be smart with notation and trying to be consistent with what people have done, which is not an easy fight. But I've tried to do this in a few papers, where if I'm dealing with a Greek letter, that is something that will be estimated. So in this equation, or in these two equations, there are 3 Greek letters. There's my variance here, which is my level 1 variance. I have beta 1, which is the mean of my intercept, and I have sigma 1 squared, which is the variance of my intercept. So those are the only 3 parameters that are going to be estimated with this model. So even though I have this B1n as my random intercept, I'm not estimating B1n for anybody. I'm just estimating its mean and its variance. Now, occasionally, especially if you read any literature in economics, where these are random coefficient models, they're going to combine the level 1 and level 2 equations. So here's the level 2 equation, and then, which is essentially B1n, and then that part of my level 1 equation. So you can combine these 2 equations. The other reason I say this is because some programs require you to program in this form. So it's important to be aware of this terminology. Of course, the other thing that you can say is that we just have this level 1 equation, and B1n, my random intercept, is distributed normally with a mean and a variance, and then my uniqueness is distributed normally with a mean and a variance. So different ways you can represent the exact same model. So the parameters are that beta 1, which is the mean of my intercept. It's called a fixed effect parameter. It's the predicted score for the sample over time. So on average, that's the score that I would predict for my sample over time. I have my level 2 variance, which is the variance of my intercept. It's the amount of between person differences in my intercept. So I have a line for each person essentially, and this tells me my lines are allowed to differ between people. And then I have my residual variance, which is the amount of noise left over after I pull out essentially this flat line for each individual. Now remember, with this model, I'm predicting that no change is happening. And the reason why no change is happening is because if you look at my equations, time is not in here. Time or age or some metric of time is not in these equations. When I move to the linear model, I'm going to now include time into my equations. So I'm assuming that time is impacting the amount of change, or essentially I'm saying time is impacting your score at that specific time. So I need to know what time it is. All right, so with the linear model, I'm allowing scores to change linearly with time. Okay, it's a very specific function. I'm allowing individuals to differ in the rate of increase, but the rate of change is constant within an individual. So you have one rate of change, but your rate of change can differ from someone else's rate of change. So for my level 1 model, I can specify it in this way, where again I have my outcome y measured at time t for individual n is a function of my random intercept, which is b1n, plus a random slope, which is b2n, multiplied by a linear function of time, plus my uniqueness. Now this linear function of time is not just time, it's not just t. I have t minus k1 divided by k2. K1 and K2 are constants that you choose. Okay? The choice is yours. Okay? They're not estimated parameters. You choose them, and they become really important. Because K1 is going to center the intercept. It's going to tell me when my 0 point is. And K2 is going to scale my slope. It's going to tell me the units for my slope, for my rate of change. Is my rate of change per year? Is it per decade? Per day? So it's going to scale that rate of change. Typically what people do, if you think about, say, using measurement occasion, K1 is often set to 1 because that would center your intercept at that first measurement occasion. And K2 is often set to 1, which would scale the slope in the original metric of time. So if you're using measurement occasion, it would be the amount of change per one measurement occasion. Okay? But if you think about different change processes, some change processes might be very slow. Okay? If a change process is very slow, it might be reasonable to use a metric of or to scale the rate of change in terms of a large time metric, maybe decades, centuries. You know, because this is the case where you can get that estimate that's 0.00 with a standard error of 0.00, and you say, oh, change is positive. You know, if you think about like how much your math ability grows in a day, okay, it's really small. I'm sorry, it's really small, right? But it's significant. It's not 0. You know, but if we're thinking about scaling changes in math, maybe a year, you know, maybe 2 years. So you need to think about how you want to scale that rate of change. In the level 2 equation, we have our random intercept and our random slope. We have 2 fixed effects parameters, which are our means, plus 2 deviations. The deviations are assumed to be multivariate normally distributed with means of 0 and a variance-covariance matrix like this, where we have the variance of the intercept, the variance of the slope, and their covariance. So there might be some linear association between the intercept and slope. It might be that kids that have higher scores initially tend to grow faster. Or it might be that kids have lower scores tend to show more growth. So there can be an association between the intercept and the slope. Now, an important thing about this association is it's just that. It's an association. Sometimes people like to make these into regressions, where the slope is the outcome and the intercept is the predictor. So if you're high, I'm predicting that you're going to change less, or I'm going to predict that you change more. This is somewhat of an issue, and the reason is that the intercept and slope, or the same set of scores, are used to derive the intercept and slope. Okay? So some people think that the intercept happens first and the slope happens second. That you have a certain score, say at second grade, and then you have a certain change process after second grade. Okay? And that's almost what the model looks like. You have an intercept, and all my data come after second grade, so, you know, it's after second grade. But my grade 2 scores are part of my slope. Okay? It's not like I take those away and I create my slope with grade 3 and on. If I do that, sure, I can use this to predict that. Okay? But grade 2 is still contributes actually a good amount of information to my rate of change. Okay? So it's an association. So in this model there are 6 estimated parameters. there are two fixed effects, which is the mean of the intercept, telling me on average how people are functioning at a specific point in time, wherever the intercept is located. And then I have my random slope, or the mean of my random slope, beta 2, which is the predicted average rate of change. I have the variance of my random intercept, which tells me about between person differences at a certain point in time, specifically t equals k1, wherever that intercept is centered. I have sigma 2 squared, which is the variance of my slope, tells me about are people changing in different ways. I have their covariance, which we just talked about, and then I have their unique variance. So how much are they bouncing around that smooth trajectory? Now, typically, when we get these estimates, people want to focus a lot of attention on beta 2 because that's the mean of the slope, the fixed effect for the slope. And that tells me, on average, are people changing, okay? But remember, you're fitting a growth model because you care about between person differences and how people are changing. So beta 2, while meaningful and important, you should also really consider sigma 2 squared to be even more important because that's the variability in how people are changing. Now, if everyone is changing in the exact same way, you might say, well, why do I care about predicting this? Everyone changes the same. If there's not much variability in how people change, who cares about predicting it? Predicting it's going to be nearly impossible if people don't vary in how they change. So you need to really pay a lot of attention to the variance of the change, because the variance of change tells me that people change in different ways. And if people change in different ways, there might be a reason why people change in different ways. And that might be an experimental manipulation. It might be some background variable, maybe gender. It might be, could be lots of things. Let's just say that, right? But if there's no variability there, it's really hard to predict it because everyone's doing the same thing. And there is some debate on the significance of the variability in the slope. First, there's the debate about whether or not the statistical test is appropriate. Okay, so that's one debate. The second is, if it's not significant, should you include predictors? Second debate. Okay, so this parameter is not without issue, but it should be a primary concern to look at it, to see if there is a decent amount of variability in how people are changing. So we'll move on to the structural equation modeling point of view. And I've heard you've had structural equation modeling for 3 hours today. So this should be easy. So the growth model as a structural equation model is fit as a restricted common factor model. So it's a very structured common factor model. So we can write it this way, where we have y sub n, which is a vector of observations for individual n on the variable y. Remember here that our data are structured now in this wide format. So we have essentially your math score at grade 2, your math score at grade 3, your math score at grade 4. So all those different math scores are organized in this vector. And we say it's equal to our factor loading matrix, which is lambda, which is going to be fully specified, multiplied by eta sub n, which are our factor scores, plus u sub n, which are our unique scores. Okay? The factor loading matrix is really important when we're specifying growth models, because the factor loading matrix is going to account for time. Okay? Now, in say our linear growth model in the multi-level modeling perspective, we put time in as a variable. Okay? Because remember, the data are in that long format. We have a variable that's time. Okay? So we can put that in as a predictor. In the wide format, our variables are organized already by time. So there's nothing about the variable, the scores in the variable, that say, oh, this is time 5. Okay? There's not a variable that says this is time 5. It's just we know this variable comes from that time point. So in the factor loading matrix, we put all the information in about time, and you'll see that shortly. The factor scores If we have a no-growth model, we're just going to have one factor. If we have a linear model, we're going to have two factors, an intercept and a slope. And just like we had a level 1, level 2 model for in the multi-level modeling framework, we can also think about this in the same way that here we have our factor scores, our eta sub n, and we can decompose them into means and deviations. Okay, so the alpha is a vector of latent variable means, and here we have the vector of mean deviations at the individual level. So with this factor loading matrix, we're really specifying the type of model that we're fitting. So in the no-growth model, if we had 4 assessments, my lambda matrix would just look like this. It would just be a series of 1s, okay? Because if we go back to our linear model from the multi-level specification, we had this, okay? And essentially, we can always write this in terms of writing out a parameter multiplied by a variable. So I can say this is 1 times b1n plus 1 times utn, okay? And so this 1 is essentially what comes out in my factor loading matrix. Okay, so you're going to see a similarity between B1n and eta 1n. Okay, because they're both going to be the intercept. Okay, in the linear growth model, we're going to have 2 latent variables. So we have the factor loadings for the first one, which again are all equal to 1 because they're the intercept, and factor loadings that vary with time, and they're going to vary linearly with time for a linear growth model. So in this case, we would have 4 time points that would be equally spaced, okay? And in each of these, we have 1 minus k1 divided by k2. And k1 and k2 do the exact same thing here that they did in the multi-level model. They're going to center the intercept, k1, and they're going to scale the slope. So as a path diagram, if I have my NLSY data, I have math 2, 3, 4, 5, all the way up to math 8. I'm going to have eta 1 here that has factor loadings that are all set to 1. Eta 2 here, factor loadings that change linearly with respect to my time metric. I have alpha 1 and alpha 2, which are my means. 2 headed arrows here for my variances of my intercept and slope, and their covariance. Okay. So, are people familiar with the triangle? Good. And I don't have to explain it, right? Does anyone know why the triangle has a 2-headed arrow on it? Alright, so the triangle is a constant. Alright. And if you regress a variable on a constant, what do you get? No. So if you have a variable and you give 1 to everybody, okay, and you regress a variable on 1, so it basically says you don't know anything about anybody. If you don't know anything about anybody, what would you guess? The mean. Okay. So if you regress a variable on a series of 1s, you get the mean. Okay. So that's why we have this latent variable here that's essentially being regressed on a constant, and that's why this is alpha 1. That's its mean. Okay? Now, this triangle has a 2-headed arrow on it that's set to 1. And a 2-headed arrow on a variable is its variance. This is a constant. It has no variance, right? But we have a 2-headed arrow here. And the reason why we have that 2-headed arrow is when we include a mean structure in SEM, we're not just modeling covariant structures. We're modeling mean squares and covariant structures. Okay? So if we have a constant, we have to think about its mean square plus its variance. So the mean square of a constant is 1. Okay, because the mean is 1, square it is 1. Okay, plus its variance, which is 0. So that two-headed arrow is actually representative of its mean square. Okay, so when we're modeling means in SEM, we are going to actually model mean squares and covariances. And there's really only 2 times that we care about mean structures in SEM. The first one is when we have longitudinal data, because you want to know, do people go up or down? The second time is when you have multiple group data, because you might want to know if one group is doing better than another group. But besides those 2 time points, we really don't care about means. So typically when you specify, say, a common factor model, that's just, based on, say, a survey of something, or a series of surveys, the mean structure that you're fitting, you're perfectly replacing by the parameters that you're estimating. So for example, if your data if you have 5 variables and you bring in 5 means from those 5 variables, you're then estimating 5 parameters to account for those means. Now in a growth model, we have 1, 2, 3, 4, 5, 6, 7. We have 7 variables here. So those 7 variables are giving us 7 means. Okay? In my model, I'm only estimating 2. Okay? So my mean structure is restricted. Okay? I'm not specifying a full mean structure. So this means I can misfit the mean structure. I can also misfit the covariance structure. Okay? Now, a while back there was a couple of talks about, are growth models just poor fitting factor models? Right? And to a certain extent, in a lot of cases, they are. Maybe they weren't fitting the right growth model, but most of the time people just talk about the linear model like that's the only model that they can fit. But growth models are essentially highly restrictive models. Okay? I'm fully specifying my factor loadings here. So if I want to think about the covariance between any 2 variables, it has to go through these latent variables in a very structured way. So that's why I say when you're looking at the descriptive data and you're thinking about the variance of the scores over time, if you're going to fit a linear growth model, those variances should change linearly. They can increase, they can decrease, but they should increase or decrease in a linear fashion. Okay, because these models are very restrictive, especially the linear model. But of course, we can relax things about these growth models. We can add a quadratic, to it. We can fit logistic models. You can do lots of things with growth models, but the linear model itself is a highly restrictive model, and that's why oftentimes it doesn't fit, because it's overly restrictive. So if we want to map the multi-level specification and the SEM specification, the vector of our factor scores eta 1 is B1n and B2n. The lambda matrix, like I said, is the functional relationship between the latent variables and the repeatedly measured scores, so 1 and our metric of time. The U vector are our uniquenesses or residuals. The alpha vector, which is the latent variable means, are our fixed effects. Psi variable, or the Cassie variable, our vector here, are our deviations. The psi matrix contains the variance of the intercept in the no growth model, and this covariance matrix in the linear growth model. The psi matrix is the matrix of latent variable variances and covariances. The theta matrix is the matrix of uniquenesses, and in this case we're going to have a diagonal elements, and essentially the unique variance will appear on those diagonal elements of that matrix. All right, so let's talk about fitting linear growth models in R. And again, this will be from the multi-level perspective. So we have the longitudinal math data. It's going to be arranged in the long format with grade as my timing metric. So we have multiple records per person. The name of my data file is nlsy_math_long. The math variable is math. The timing variable is grade, and we have an ID variable called ID. Now in R you can use LME4, which is a linear mixed effects program. You can use NLME, which is another linear mixed effects program. And in both of these packages, there's a linear mixed effects procedure and a nonlinear mixed effects procedure. Okay? What I decided to do is to use the nonlinear mixed effects procedure. Okay? Now the reason why I do this is because when you're programming the nonlinear versions of these software, the programming becomes very clear. Okay? You specify the exact model you want to fit. When you're using the linear mixed effects modeling procedures within these packages, you lose some of that. You lose some of the explicit nature of the programming. So the programming is a little bit more intensive, not much more, but it's a little bit more intensive. But the nice thing about it is that you can be sure of what you're doing because you have to specify everything. So what I'm using here is the NLME package. I'm in R. And one of the reasons why NLME is kind of the older version of LME4 in terms of packages. The reason why I chose to use this procedure is because in the newer package, the nonlinear version could not fit a linear model. And I was troubled by that because I thought this should be easy. And so that's why I used the older software, but you know, the older software is good. The new one's good, it can do some extra things, but I had some other issues with it too, but that was the main issue. So we're gonna call the library here, NLME, so that brings it into our setting. I'm creating this object, which is gonna be for my no growth model. I have NLME, which is my procedure, which is the nonlinear version. I say math is a function of beta 1 plus d1n. Okay? So beta 1 plus d1n, that's my level 2 equation that I specified when I was writing out my multi-level models. My data is the NLSY math long data file. My fixed effect parameter is beta 1. Okay, that's my fixed effect. My random coefficient is d1n. Okay. My grouping variable, which is how I'm clustering my observations, is based on ID, which is the identification variable. I provide a starting value for beta 1, which is going to be 40, and I set NA action to NA omit. Now, for some reason, in R, with this package, if you have somebody that is missing the outcome, okay, say they're just missing the outcome at one time point, the person shouldn't be dropped, but that observation for that person should be dropped. Okay. Now, if you don't put this NA.action statement, this procedure won't run if you have data like that, which is kind of just annoying. So just set NA action to NA omit. We can ask for a summary of the object that will output your parameter estimates, and you can ask for intervals of the object, which will give you confidence intervals for your random coefficients. So here's some of the R output. It begins with giving you some likelihood-based fit indices. So it gives you the Akaike information criteria and the Bayesian information criteria. These two information criteria can be used to compare models. They have no absolute scale, so they can be however high or however low. Okay, it doesn't give you any information about how well the model fits the data. But if you're fitting two models and you want to know which one fits better, you can use these. It also gives you the log likelihood. Okay, this is the log likelihood here. The Bayesian information criteria and the Akaike information criteria are based on the log likelihood plus a penalty. So they're -2 times the log likelihood plus a penalty function. The penalty function for the AIC is twice the number of parameters, and the penalty function for the BIC is the natural log of the sample size times the number of parameters. So these two information criteria can actually be used to compare models that are not nested. okay, which is nice. Okay, they have a penalty for how many parameters you're estimating. So the more parameters you're estimating, the more you'll be penalized. Typically, people will follow the BIC more closely than the AIC because the penalty for the BIC is greater. The next parameters, the first two parameters we have are the random effects parameters. These are in terms of standard deviations. So D1N, the standard deviation is 6.8, and the standard deviation of the residual is 10.8. Okay, so again, the residual is that level 1 residual, that UTN, that variance sigma u squared, and in terms of standard deviations. And D1N, this is essentially sigma 1, the standard deviation of the intercept, of the random intercept.
Oh, I'm sorry. You said something about comparing the non-nested models, following the BIC versus the AIC. I missed some of it.
Sure.
I heard non-nested, and then I missed the beginning of it.
Just got caught on non-nested,
yeah,
huh?
Yeah, that's what I thought. But I missed the beginning. Can you
Sure. Right. So the AIC and the BIC are both based on the log likelihood plus a penalty function. The BIC is what people tend to follow because it has a larger penalty function, which is the natural log of the sample size times the number of parameters.
And that's something specific to R?
No. Yeah. The only fixed effect parameter we have here is beta 1, which is 45.9. Again, in this case, we have a standard error, a t-value. But really, we don't care if this is different from 0, okay? Because this is an intercept, okay? You know, if you added 10 points to everyone's scores, the intercept would be 10 points higher. It would be further away from 0, okay? So looking at the significance of this intercept really is not so meaningful. What people really want is they want to know the significance of this variance. This tells me about between person differences in the intercept. And you'll notice that R does not give you a standard error, does not give you a t-value, does not give you a significance level. And this goes back to some of the controversies about estimate or determining the significance of variance parameters in multi-level models. What they want you to do is they want you to fix that variance to be 0 and then do a likelihood ratio test, okay? So what they want you to do is to have this model fit, to take twice the log likelihood or twice the negative 2 of the log likelihood, and subtract the 2 from the 2 models that you fit and see if they fit similarly or not. If this model fits much better than when you force it to be 0, then it says this variance is important. Now, that's a fine procedure. When you get to models that have more than one random effect, it becomes a little problematic, because when you force a variance to 0, you're also forcing the covariance to be 0. So it's no longer a 1 degree of freedom test. It becomes a 2 degree of freedom test, which makes it a little bit more tricky to kind of figure it out. But that's basically the reason why R doesn't do that. If you ask for intervals, I don't have the output, but I had that interval statement from R. That will actually give you a lower and upper interval for the variances, which you can then use to kind of give you a sense of whether or not there is variance in that intercept. To fit the linear model, we just simply write out kind of that combined equation. So we say math is a function of beta 1 plus D1N, that's my random intercept, plus beta 2 plus D2N, which is my random slope, multiplied by grade minus 2, okay? Now, remember, grade is my timing metric, but my first scores are in second grade. So I decided I wanted to center my intercept at second grade, because that's what was meaningful to me. So I subtracted 2 from grade here, okay? So my intercept will be indicative of scores at second grade. If I don't subtract 2 from grade, where is my intercept centered? Kindergarten. I don't have any data in kindergarten. I'm just making projections backwards. Now, I'd rather have my parameters to be representative of data I actually have. Okay, so that's why I'm centering the intercept in second grade. My fixed effects parameters are beta 1 and beta 2. My random effects parameters are D1 and D2N. My clustering variable is ID, and then I provide starting values for my fixed effects. Now, to get starting values for the fixed effects, you can do a couple of things. The easiest one to do is just to fit a regression model to your data. Fixed effects are about averages. Okay, so if I just fit a regression model, a linear regression model to everyone's data all collapsed together, I should get a pretty good estimate of where they will be in second grade and how much they're going to change. Now, starting values for linear models, not so important. Starting values for more complicated models become very important. So as your developmental process becomes more complex, you need to provide more, you need to help the program out a little bit more. And so that's where coming out with good starting values becomes very important. So here's the output from the linear model. Again, we have our information criteria and our log likelihood values. These, if we were just to look at the BIC, for example, the BIC for this model is 15,983. And for the intercept-only model, it's 17,515. So the fact that the BIC is lower for the linear model gives more support for the linear model. It's basically telling me the linear model represents my data better than the intercept-only model. I come down to my parameters, and we'll start with the fixed effects. So beta 1 is 35.2. So that's my predicted mean, the predicted mean of my intercept. So in second grade, on average, I'm predicting students have a score of 35.2. And then beta 2 is 4.3. Okay, so on average, I'm expecting kids' scores to increase 4.3 units per year. Okay, it's per year because grade is scaled in terms of years. So 4.3 points per year. And again, I'll probably care whether or not this is significant from 0. Because if it's not significant from 0, it says overall, people didn't change. But again, that's just overall. If we come up to my random effects parameters, I have the variance of the intercept, which is 8.0. So that's about between, or sorry, the standard deviation of my intercept, which is 8.0. So it's about between person differences in scores in second grade. And the standard deviation of my slope is 0.86. And again, that's about between person differences in the rate of change. The last, this is in terms of a correlation. The correlation between the random intercept and the random slope is minus 0.03. So there's really very little association between your scores in second grade and how you're predicted to change based on these data. The last random effects is the residual. And the residual is about 6, which again is about variability in scores that's not accounted for by this growth model. Another thing that you can look at when you're comparing models is this residual. The residual for the intercept-only model is 10.8, and for the linear model, it dropped down to 6. So we're capturing much more variability in how these scores are changing over time with this linear growth model, which, I mean, we would of course hope after we looked at the plot and we saw that there was, growth over time. If we move to the to Mplus, our data are now organized in the wide format. We have a variable that represents the score at each grade, so Math 2 all the way through Math 8. And here's a script for the no-growth model. So with this data, the data are now in the wide format. Okay, so I'm reading in a different data file. It's the same data restructured. I have all the names of the variables that are in my data set. I have my missing data code here, so I have a dot to indicate a missing value. The variables I want to use are Math 2 through Math 8. The analysis, this is kind of, when I first started using Mplus, type equals mean structure, you used to have to write, but now it's the default. So you really don't need this. But this coverage equals 0 becomes important. Coverage equals 0 refers to the covariance coverage. Okay? The covariance coverage is the proportion of individuals that contribute to the estimate for each covariance. Okay? Now, the nature of my data is that everyone was essentially assessed every 2 years. And we saw when we looked at the descriptive statistics that basically no one was assessed in grade 2 and grade 3. Okay, so there's nobody there. So if there's nobody there, Mplus won't run. Okay? The lower bound that Mplus puts on covariance coverage is 10%. Okay? So since my covariance coverage is less than 10%, I'm going to put coverage equals 0. Because without it, Mplus wouldn't run. Okay? Now I specify my model, and I'm trying to specify my model as complete as possible. Mplus decided it wanted to give you lots of shortcuts for writing syntax. Okay? I encourage you not to use any of them. All right? Because Mplus will do things that you do not want it to do. It does this to me all the time, and I still hate it. It's a wonderful program, and I hate it at the same time. You know, for example, like Mplus will covary all latent variables, unless you say not to. If you're fitting multiple group models, Mplus has a certain default multiple group model that it specifies. If that's not what you want, it's going to do it anyway, unless you tell it not to. So it's somewhat of an issue. You could write like 3 of these lines and be fine. But I try to write everything as much as possible. So eta 1 is going to be my latent variable intercept. It's indicated by my math variables with all factor loadings that are fixed at 1. I then ask for the variance of eta 1, the mean of eta 1, so anything in brackets are reflect means and intercepts. And then here I have math 2 dash math 8, and in parentheses I have theta. So math 2 dash math 8 refers to the variances, or in this case the unique variances, of my outcome variables. And I am going to constrain those unique variances to be equal across time. That's what's done in multi-level modeling programs. So I'm doing this to be consistent. Again, if this is not the case and you force this to be the case, you're going to get biased parameters. So you might want to investigate this procedure or investigate this constraint as much as possible. Lastly, we have math 2 through math 8 at 0 contained within brackets. So that's going to refer to the intercepts of my observations, okay? And those intercepts are fixed to be 0, because in the growth model, the mean structure comes from the latent variables. In my output line, I'm just simply asking for sample statistics. So when you get the output from Mplus and most structural equation modeling programs will provide you more information, okay? Which is one of the benefits of SEM. It gives you a potential sense of how well your model actually represents your data. We have the information criteria very similar to what we had before. These values should basically be spot on to what we had before from NLME. It also gives us a sample size adjusted BIC, which I found kind of tracks like the AIC a lot. It gives us a chi-square test of model fit. This is a test of whether or not your model fits perfectly. Okay? Your models will not fit perfectly. Okay? So typically it will always be significant. And then it gives us some information about practical fit. The RMSEA, in this case, is 0.24. The RMSEA, lower values indicate better fit. Sometimes people have put cutoffs at 0.05, 0.08, 0.1. It's kind of like how you're feeling on the day, which one you're going to do. You know, I feel like whatever model you fit, you're going to try, and you like it, you're going to try to justify it in some way. So just change your cutoff value. They're all arbitrary. Okay? There's no. It's not 0.05 like significance 0.05. Okay? It's all arbitrary. It also gives us a CFI and a TLI. And the thing to know about the CFI and the TLI is that for longitudinal data, these are incorrect. Okay? So with longitudinal data, the CFI and the TLI are not correct. Okay? And that's why sometimes you see negative values, because it's about how non-correct it is. Okay? Basically, to get a CFI and a TLI, you fit a null model. In a null model, you're estimating the variance of each time point, and you're estimating the mean of each time point, and you're not estimating any covariances. Okay? So for these data, I have 7 variables, so I'd have 7 means, and I would have 7 variances. So I'd have 14 parameters in my null model. How many parameters do I have for a no growth model? 3. Okay? So I have less parameters in the no growth model than the null model, which is not how it should work. You should always have less parameters in the null model. So if you want to calculate the CFI and TLI properly, you have to kind of do it post hoc by hand, okay? Which is not a terrible thing to do. Typically people will just report these and not say anything, but that's typically what people do. We come down to our estimates. We have the mean of eta 1, which is 45.9. That's the mean of the latent variable intercept. The variance of the intercept is 46.9. That's about between person differences. And if you're comparing this to the output from R and NLME, R and NLME was reporting standard deviations. So these are in terms of variances. And the residual variance, you see that they're all the same because we force them to be the same, and they're about 116. So there's a lot of variability around these flat lines, which is another indication that this model doesn't reflect the data well, which is essentially what we wanted to say anyway. To fit the linear model, we start out pretty much with the same information about our latent variable intercept. We define it in the same way. And then we bring in eta 2, which is going to be my linear slope. The factors, or the factor loadings for the linear slope, are going to start at 0 and go all the way up to 6. Okay? They're starting at 0 because that's where I want to center the intercept. That's essentially grade minus 2. And they go all the way up to 6 because I want to scale my intercept in terms of years. If I made these 0.1, 0.2, 0.3 all the way up to 0.6, I'd be scaling my intercept in terms of decades. Okay? So it depends on how you want to think about the scale of your slope. I then have the variance of eta 2, the mean of eta 2, and its covariance with the intercept. Now a couple of extra things that you can output from Mplus. We can have this plot command, which is plot 3, type equals plot 3, and the series command is all my observations with respect to eta 2. Okay? What I'm saying with respect to eta 2, it basically takes the factor loadings for eta 2 as the x-axis. So it's going to plot some trajectories for me. The other thing I do here is I save the factor scores. Okay, and you'll see why I save these factor scores. I think saving these factor scores is a nice way to think about or evaluating model fit. Okay, so I'm saving these factor scores. If we come to the output for my linear model, my chi-square dropped to 204. Okay, I can compare my chi-square between these two models with a likelihood ratio test. My RMSEA is now 0.08, so now I can jump for joy because it's less than 0.08, almost. The CFI and TLI, look better now, but still they're not proper. Yes.
Are those always underestimating?
Typically with growth models. Yeah, so the model that you should actually fit for the null model for longitudinal data should be that you have the same mean across time, and then you have the same variance across time. So it's a 2-parameter null model. So if you fit that model, you can calculate the CFI and the TLI, and it would look much better because that model is going to fit much worse than the null model that they're fitting. And the CFI and TLI are really about how much better your model is from the null model. So it'll make your model look a lot better. If we come down to parameter estimates, we have the means of eta 1 and eta 2. So 35.26, that should be the same value we got from NLME. That's your predicted mean in second grade. Eta 2 is 4.3, that's the predicted annual rate of change in the math scores. We have the variance of eta 1, 64.56. significantly different from 0. The mean of 8 at 2, also significantly different from 0, suggesting that kids differ in how fast they change. Some kids are growing faster than others, which is great because we might want to include something that would predict that. We then have our unique variance down at the bottom, and my covariance. This is in terms of a covariance, 8 at 1 with 8 at 2. If you ask for a standardized output, you can get the correlation between the intercept and slope, which makes it, of course, easier to talk about that linear association. All right, so we can compare these two models, of course. They're nested. One model is a restricted form of another model. So these two models are nested. We can do this based on the -2 log likelihood, and we can do this based on the chi-square. You'll get the exact same information. What you simply do is you take the difference between the -2 log likelihoods, and that difference is going to be distributed as a chi-square statistic with degrees of freedom equal to the difference in the number of estimated parameters. So the difference between the two -2 log likelihoods is about 1,500. I've only used 3 more parameters, so I can say with confidence that the linear model fits better than the no growth model, which I think you could all tell me, before. Now this is where I want to pull in the factor scores from Mplus, okay? And so you can pull in the factor scores from Mplus, which are essentially going to be estimated scores of the intercept and slope for each person. And I find this to be very useful. So what you can do is you can bring these factor scores in to R or to SAS or to whatever program you're using, and you can use them to create predicted plots. And you can also use them to create residual plots. When you do regression, looking at a residual plot is important. You want to understand where your model is kind of misfitting. We can do this same thing with these mixed effects models or these structural equation models. Now, this is code in R. The output from R automatically includes the individual estimates. You just have to pull them out. I'm not going to go through the code too much, but basically what I'm doing here is I'm calculating an estimate for each individual of their intercept and an estimate for each individual of their linear slope. And I'm creating a predicted value based on their predicted intercept, their predicted slope, multiplied by my time metric, which is grade -2. And then I calculate residuals as simply the math scores, the observed scores, minus the predicted values. From these scores, I can create plots like this. So this is the plot, this is what my linear growth model is expecting my data to look like. Okay? My data obviously don't look like this, but this is what the linear growth model is expecting my data to look like. And it's somewhat easy to think about this with a linear model, but if you have like a quadratic model or a cubic model and you're trying to understand how it really looks for each individual, how they differ, these plots are very useful. So obviously we have a mean of these intercepts somewhere around 35. We have an average rate of change of about 4 points per year. But somewhat more important, we can make this plot. These are the residuals. So these are the residuals for each individual over time. And what's the first thing that jumps out at you with this plot? What do you think? Do you think the mean is 0 at all time points? Probably not, okay? It looks like it's a little low down here, goes a little high up here, and gets a little low down here. So what do you think that means? If my residuals have a pattern to them. Well, that's the residuals. It's not linear, right? I mean, the linear model fits better than the no growth model, but this is kind of telling me that I'm missing some sort of bend in my trajectory. Okay, my data are not perfectly linear. The mean changes. The mean begins negative, it goes to 0, then it becomes positive, and it comes back down. So what this really tells me is that kids are probably actually growing faster early on than they are growing later on. So they're probably increasing faster and then beginning to slow down. So maybe an exponential model might be more appropriate. So plotting these residuals can really start to tell you about where you've kind of gone wrong with your model. The other thing to look at, of course, is the variances. The variances, they seem approximately equal over time. I put a constraint in there that said that they were equal. So this kind of, agrees with that general idea that the amount of residual variability at each time point is approximately the same. Of course, I can relax that constraint in SEM, very easily do a likelihood ratio test. But doing that in multi-level models is not so easy. What's that?
That's not true. So that you can only found residual matrix in multiple models as well.
In some,
Not in LME4, but in NLME, there's correlation structure. You could have increasing variances as a function.
right. Like proc mixed is pretty good with it.
Yeah.
NL mixed, not so much. I know there's a paper about using NL mixed with it. Very complicated.
Proc mix will do it.
Yeah.
NLME has a fair bit of capability.
Does it? Okay, good to know. Thank you. So yeah, so you can do these things. It's a little bit more complicated, but What about What about? They're all different. They're all different. But right, you can do this, and it's good to test for these things. Absolutely. All right, some important considerations. We talked about the variance being equal over time. This is an assumption. You can allow for flexibility in these in a pretty straightforward manner. We talked about centering the intercept in grade 2. You don't have to center it at the first time point. You can center it at any time point you want. The important thing is that you center it at a point that you care about. Because for this model right now, we have no predictors. So it's mostly informational. But there's going to be, the next thing you want to do is you're going to want to start predicting things. So the question is, do you want to predict scores in 2nd grade? Do you want to predict scores in 4th grade? Do you want to predict scores in 8th grade? Okay, because remember, we're going to be predicting the intercept, predicting the slope. We want to predict things we care about. If you're doing an intervention, you might want to predict how people do before intervention. But what you might care more about is how people are doing at the end of the intervention. So it might make sense to center your intercept at the end of the intervention, because that's where you care about things. So you should center the intercept at a place that you care about predicting. Of course, where you put the intercept, it doesn't affect model fit in any aspect, but it's just about making your parameters more interpretable. We talked about the scale for the slope. We scaled it in terms of years. We thought that was meaningful for these outcomes. You can, of course, change it to seconds, minutes, days, weeks, months, decades, millennia. Depending on whatever you're studying, you might want to think about how quickly something is actually changing. Again, if you scale the slope in a different way, it's not going to impact model fit. It's just going to impact your parameters. Some benefits of the various approaches. You saw some of them here. The standard SEM approach gives you that additional fit information. Now, it's not to say that you can't calculate this. If your data are structured in a discrete time metric, you can calculate an RMSEA from a multi-level model. Okay, you can do these things. So it's not to say that you can't do these things, but the programs, typically do them, or they typically don't do them. And the multi-level programs typically don't give you that fit information. For a while, people were kind of saying, well, if you fit a growth model in SEM and it doesn't fit, just tell the journal that you fit it in multi-level models, and then you didn't know. Because, right, the information that the multi-level model programs give you, you can use that information to say one model is better than the other. But that information by itself doesn't tell you how well it fits the data. And the SEM gives you that information up front. Sometimes you don't want to hear it, but it at least gives you the information up front. But it's not to say that you can't calculate it. The reason why the multi-level programs don't give you this information is because generally they're more flexible for these types of models. For example, they can easily handle people that vary in their time metrics. We can use their exact age for the time metric. If I wanted to do that in SEM, I would either have to create a really big data set, which Mplus wouldn't let me run through anyway, or I can use some of the special programs in Mplus, which would basically turn it into a multi-level program, and it wouldn't give me an RMSEA anyway. So because of the flexibility of the mixed effects modeling framework, it can't give you things all the time. But it doesn't mean you can't get them if you really wanted them. Like I said, the linear growth model is an appropriate starting place for a study of change. I don't think people should stop here. Of course, people like to jump to quadratics if they see some bend. I'll tell you right now, I hate quadratic models because the parameters can be very challenging to interpret. I like people moving more towards models that have parameters that are a little bit that have parameters that are a little bit more meaningful. People usually don't care about acceleration when they're fitting growth models, but a parameter of the quadratic gives you some information about acceleration. You can always compare more complex models to simpler models. Some of these models will be nested, like the quadratic model and the linear model. Some of them might not be nested, but you can also use the information criteria. You might want to consider group differences, where there are group differences in the rate of change, group differences in the patterns or the shapes. Right now, everyone's linear, okay? But you can begin to fit models where people show different shapes of the trajectory, which I think becomes a really interesting question. It's not just about magnitude of change, but it's about how you got there. All right, so why don't I'll take questions and then we'll take a break.
So on the patterns of change, what if, instead of looking at weight, which always goes up, you're looking at BMI, and you might have one group that is going up, but another group that's going down over time? Is that something that you pull those out, and then you could use these models to track the weight loss over time?
Couple things. So you could do that. You could pull people out if you think they're going a certain direction. You can look for growth. You can look at growth mixture models, which will try to cluster people based on how they're changing. So if you think there's two groups of individuals that are changing in different ways, you can use a growth mixture model to really try to, get that support from the data instead of putting people in these groups ahead of time. If there's a variable that you think affects the shape of the trajectory, you could potentially fit multiple group models. There's some other models that I've been working on a little bit that would allow the shape to differ based on some continuous metric. But typically the multiple group and the growth mixture models are probably the most reasonable.
I have one more question.
Sure.
If you're going to impute, does it make sense to do it in the wide?
Couple of things. So there's some programs that do multi-level imputation. There's not many of them, but there are some. There's one in R that does multi-level imputation. And I know Craig Enders has published a little bit on multi-level imputation, and I know they're working on 3-level imputation. So you can impute in that form. I think it's easier to impute in the wide form because you see the direct connection between the person over time. The question that you're going to end up with is whether or not you need to impute. And I think it's somewhat based on the sparseness of your data. If you stretch the data out wide and you have 90% incomplete because of how you organize the data, imputation not going to work so well. But you can still use full information maximum likelihood in those cases, and that typically does pretty well. So yeah, I would probably go with the wide format. Other questions?
I don't know why I'm getting caught up on this, but so you said for an intervention, and you're curious to see how people end up. Let's say
Sure.
12-week intervention, and so you're going to center the intercept
At the end.
at the end.
Right.
So that'll give you that intercept parameter, but the slope, the change over time, will be the same as it would be otherwise.
Yep.
Okay.
And you can do a couple of things. And again, it all depends on the information that you want to pull out. So you can write, so if say you have your model, And then in here, we're going to say, is time, say it's a 12-month intervention. So you subtract 12 from your time. So at 12 months, essentially is your 0 point. And your time metric goes from, minus 12 to 0. So now your intercept, this B1, is now representative of the level of people's functioning at the end of the study. Now B2 is still the linear slope. So it's just like taking, this line and saying I care about this parameter or I care about this parameter. Now, another thing that you could do is say you don't really care so much about the slope. I don't know why you might not care about the slope, but say you don't care about the slope. You don't have to have a slope in a linear growth model. You can have two intercepts. So you can say I care about where they start and I care about where they end up. And in between, I have a linear growth model. And this is something that John Willett wrote, that was contained in one of the papers that he wrote. But again, it's a linear model, so you get two parameters. Now, what two parameters you get, that's up to you. You can get, typically you get an intercept and a slope, but you can get two intercepts.
How does that change your interpretation? Well, maybe in a non-linear it would make a difference, but in a linear it would just be talking about it in reverse.
Right, absolutely. And it depends on what you want to predict. Because the next step in these models is to really have predictors of these two parameters. And so if you think the intervention, if that's your big thing, you want the intervention, you want to see if it predicts the intercept and the slope, you might want the intercept to be at the end, because that's after the intervention actually took place. If you want to see if randomization worked, maybe you care about the intercept being here to make sure that groups weren't different at the beginning. So it's all about just getting the parameters that you want to get out of the model. But it's not going to change the model in any sense.
And you can derive, if you have the two intercepts, you can derive the slope.
You can always derive the slope.
So you can, this is just sort of what you're outputting.
Right. But it kind of gets to that idea of, say you have three groups in analysis of variance. How many comparisons can you make? Two. You have 2 degrees of freedom. You have three groups, gives you 2 degrees of freedom. So you can only make two comparisons, right? So you can compare 1 and 2 and say 2 and 3. Now you can derive 1 against 3, but you shouldn't be getting that much information out. And that's where people get, statistics become really annoying because they make it all confusing. So say you have three groups. So say you have three groups and you say 1 is different than 2 and 2 or 3 are the same. Okay, and you're like, okay, that's fine. And then you figure out the third one and you say and 1 and 3 are the same. Wait, 1 and 2 are different, 2 and 3 are the same, and 3 and 1 are the same? You're like, that's stupid, right? Because you got too much information. You abused your data too much. You only get two comparisons, so you should choose the comparisons that you want to know. And that's why, typically we might dummy code and because those are the comparisons you want to make. All right, why don't we take a break for another 10 minutes and then I think we'll have one more combination talk. Thanks, everyone. All right, so what I thought would be best is to focus on the fourth set of slides that I sent you about growth mixture models. I guess I was a little overambitious. Maybe I just spoke too much. So I figured I'd focus on this because we haven't talked much about growth mixture models. And I think this is a more complex issue as opposed to adding covariates as predictors of your intercept and slope. So we'll talk about growth mixture models. We'll get through an introduction. We'll work a little bit, mostly in the SEM framework. There's nothing about the multi-level modeling framework that says you can't fit mixture models. It's just that most of the programs you can't fit mixture models. But there's nothing about the framework. You can actually specify mixture models in NL mixed, which I've done, but from my experience, the information I get out of NL mix is not consistent with what I've gotten from other programs, so I've been a little questioning. It's not drastically different. You know, the fit is not terribly different, so I see where it's going, but it wasn't consistent with some of the other programs that I've used. So we're just going to focus on SEM and Mplus. Mplus is definitely the best program for doing these analyses. It's the most comprehensive. It's been doing these analyses for the longest amount of time. It provides the most information for these types of models. So it's really the gold standard when it comes to fitting these models. We'll fit some models. We'll talk about an approach to fitting models. We'll look at model fit, model comparison, trying to figure out how many classes there are in the data, etc. So when we are fitting growth models, we kind of have this implicit assumption that our intercepts and slopes are normally distributed. Okay, which makes things nice. You know, when you're in SEM, you're typically assuming multivariate normality. So you're assuming that your latent variables are normally distributed, so they can be described by means and variances. What this also somewhat implies is that it's drawn from a single population, because we always think if we have a single population, we have a nice normal distribution. If we add a covariate as a predictor of the intercept and slope, our assumptions change a little bit, because what we assume is that the residual variance of the intercept and slope are normal, not that their whole distribution is normal. If we do multiple group models, a similar thing happens. We assume things are normal within each group, but if we were to combine our groups together, we would not assume normality. The growth mixture model comes at it from a different perspective. It says that, you know, there might be these groups in our data, but they're not well defined in terms of the variables that we have. If they're well defined in terms of the variables we have, we should fit maybe multiple group models where we're in charge. We say these people are in this group, these people are in this other group, and then we fit our models. And that's easy when we have variables that are kind of grouping types of variables. And we have ideas about differences in, say, trajectories based on those groups. But there are times when we just have no idea, okay? But we think something might be going on there where people are changing in fundamentally different ways. And the growth mixture model is essentially like a search procedure to kind of search for groups, okay? It's very exploratory. That's one thing that people, you know, somewhat grapple with, because, you know, exploratory is almost like a bad word, you know, when you're doing analyses. Oh, you're exploring your data? It's okay, just tell people you're doing it. And this is very much exploratory. You know, I'm giving it some basic information about what I'm expecting. I'm giving it basic information on maybe how many groups there are and what my model looks like. Okay, so I am giving it some information, but I'm not telling it who's in what group. All right, this is a search. Sometimes it might be useful actually to use these methods to just kind of get a sense of whether there might be groups in your data. Maybe you don't think there are any groups in your data. Maybe you fit this model to try to see if there are any groups, and it might say, hey, there's no groups. And then you can say, great, I didn't think there were any groups. I have no groups. Usually that's not what people do, but you can use this to kind of justify that you have one group. But what the statistical part of this model is doing is it's simply just trying to account for non-normality. If you have non-normal distributions, mixture models will do its best to account for that non-normality. If we're using maximum likelihood, you're assuming everything's multivariate normal. Okay, so you're doing your best to account for this distribution with a normal distribution. Now, if it doesn't fit so well, you can always do better by adding another normal distribution. Okay, and that's where this procedure becomes a little scary, because you can always find something. You know, your data are never perfect. You can always search, and if you search hard enough, you might actually convince yourself that you found something, when in fact what you found was really nothing. And that's where some of these struggles come from. But what I try to do is I try to have a very systematic search procedure. Okay, a search procedure that I can justify. And when I write a paper on it, I tell people what my search procedure is, and I carry it out. Different people use very different search strategies. You'll see the models that I fit, I'm fitting maybe like 7, 8 different models. Okay, I've seen other people give talks on growth mixture models and said they fit about 260 models, and I'm just like, and this is the one you chose, you know, like p less than 0.05. You know, I mean, like, you know, if you keep on searching, you'll find something, you know, unique and interesting about your data. But the question is whether or not what's unique and interesting about your data will also be unique and interesting about someone else's data. And obviously replication of these types of results is very important. And that's the other thing that we should think about, is when we're choosing models, we need to think about, you know, a model that is likely to replicate, because that's our goal. You know, not just account for our data as best as it can, but a model that will actually help another researcher when they're doing their work. So we have essentially, say, or one of our outcomes, or maybe an intercept or a slope, has this solid distribution, which is non-normal. So if you just fit a growth model, we're trying to account for it, we're trying to make it as normal as possible. But it's always easier, if you have some sort of non-normal distribution, to account for it with two normals. Okay? And what this is a mixture of two normal distributions. And typically mixture models are fit as mixtures of normal distributions, because you can kind of put normal distributions together in lots of different ways to get all sorts of different shapes. There's one project that I've been working on with some people in Virginia, where we're looking at school readiness, and we have these, you know, say 8 indicators of school readiness, and we're fitting mixture models to these to try to figure out, you know, if there are different clusters of individuals with certain skills, and try to figure out how they do over time. And when we first started running this model, you know, like the PI of the project is like, well, look at this, you know, visual spatial skills, like that's what seems to be most different with these different clusters. So these visual spatial, they must be really important, because that's the variable that's most different in all of them. You know, and then you look at the frequency or the distribution of visual spatial skills, it has the worst distribution. The reason why it has the largest effect is because it's the worst distributed variable that you have. You know, so then someone's like, well, why don't you know, try to normalize it? Okay, so, you know, the person normalizes it, and lo and behold, it has no effect on the cluster membership because it's normal. You know, so it's like, well, what do? You know, if you try to normalize anything, you're not going to get mixtures. You know, but if you have a really terrible variable, that's the variable that's going to tell you have mixtures. So it's, you know, it's this, you know, I don't even know what type of game it is, but it's a terrible game to play. So what we're trying to do here is be systematic and be thoughtful about searching for unobserved groups. Essentially, there's a categorical latent variable that's trying to put people into groups. We don't know who actually belongs to which group. So we're trying to use the information in our data to give us a sense of who belongs in what group and how likely they are to belong in one group. Now, the simplest case of a mixture model is if you have one variable, okay? You have one variable and you need to put people into groups, okay? People do this all the time, especially people in medicine. You know, they want to say, you have high blood pressure. You know, there's a cutoff, right? What's the cutoff? If you're over like 120/80, you know, you go on this side, you have high blood pressure, and we're going to put you on some medicine, okay? So they create a cutoff on one variable and make a decision on it, okay? Now, their decision is not like, hey, I'm like 60% sure you have high blood pressure. They're like, you have high blood pressure, you know, so you're over there. With a mixture model, we're trying to account for the whole distribution. And if somebody is close to what a cut point might be, we basically acknowledge the fact that we're not really sure. Maybe it's 60% in this group, 40% in that group, but it's not like 100 and 0. If someone's if someone's blood pressure is really high, maybe it's like 95.5, but we account for the fact that we don't know. Okay, and that's a really important thing with mixture models, is that we're trying to be careful about saying that people are in groups, because even with this model, they're not in groups. There's a probability that they're in a group, and we're trying to figure out that probability. So they're post hoc, they're exploratory, they provide some circumstantial evidence for unseen groups. Remember, nothing is definitive. And it becomes really important when you think about non-normal data. In psychology and lots of disciplines, we have non-normal data. Does that mean there are groups under everything? Maybe not. Probably not. And that was some work that Bauer and Kern did in a psych methods paper that was commented on by a bunch of people. Basically, they took normal data that they simulated. They performed a transformation to make it somewhat slightly non-normal, somewhat skewed, slightly kurtotic, and then they fit mixture models to it, and lo and behold, they found groups. So they were like, look, this was one group, and now this procedure is telling me I have groups when I don't have groups. I just have one group. And it's a little bit of a balancing act, because it's like, all right, you had one group and then you transformed it. So, a mixture model will fit better because it fits better to the transformed data. But it was still kind of generated as one group. So that's where you have to think about non-normality. What is the reason why you have non-normality? Is it because your measurement is terrible? Are you not targeting your participants well? If I give people in here a third grade math test, hopefully everyone's at the top, but it's probably maybe a little skewed. So things are not going to be perfect, but it's because my measurement was terrible. It's not because there's tons of groups of people here. It's because I have bad measurement. So you need to think about why you might have non-normality. There might be nonlinear associations that you're not accounting for. It might be poor measurement. With poor measurement, you can try to fit some factor models. Factor models try to clean things up a little bit. Our results with factor models were a little bit more promising, that you weren't kind of finding so many groups with factor models. And that's because if you have, you need multivariate measurement. Multivariate measurement's better than univariate measurement. And the type of non-normality has to be consistent across indicators to kind of move up to the factor level. But you need to think about alternative explanations for mixture models. So I pulled a sample of data from the early childhood longitudinal study. I just selected a 10% random sample, so I still have a good sized sample. It's about 2,000 people. And I just took 4 time points. And these are the children's weight. So here we have weight in pounds. We have their grade when they were assessed. 0 is the fall of kindergarten, 0.5 is the spring of kindergarten, 1 is the fall of first grade, 1.5 is the spring of first grade. And you can kind of see that there's a big cluster of individuals here. And there's fewer people up here, but from this you can tell that my distribution is non-normal. Okay, it's going to be positively skewed, which may make some sense here. So we can write the growth mixture model in this form, where we essentially have our growth model, but everything is superscripted by a K to indicate that it's class dependent. So essentially what we have here is we have a vector of observations for person N in class K. We actually don't know who's in class K, but we write the model in this general form. We can also say that the factor scores, which is for person N in class K, are dependent on the means in class K and deviations for that individual in class K. Now the way that I wrote this model is essentially that every matrix is class dependent. So you'll see on most of my matrices I have a class dependent. So alpha sub K psi k, theta k. The only one that I didn't do is lambda. And the reason why I didn't do lambda is because for right now, or for right now here, I'm dealing with a linear model. Okay, I didn't want to add complexities with nonlinear models, but I'm just dealing with a linear model. So in my lambda matrix, I'm specifying a linear model. There's nothing that prevents you from making lambda class dependent. I find it extremely interesting to make lambda class dependent, because then you're saying the structure of change is different for the different classes, not just the parameters of the linear model. But all the matrices here except for lambda are class dependent, and when you specify the models, you don't have to specify that everything's class dependent. You can be systematic about your search, and that's where I think it becomes very important. So like I said, lambda is not class specific. We're just dealing with linear models. It can be class specific, and like I said, I find this to be very interesting when it is class specific. So what we kind of came up with, and this kind of followed our, some thoughts that we had about multiple group models, is that we are very systematic in the models that we specify. We begin with a model where all the parameters are invariant. It basically says that everyone belongs to one group. So there are no classes. It's one class of individuals. We then say, all right, the classes may differ in the means of the latent variables. So the mean of the intercept, the mean of the slope may vary over classes. This is the model that people typically fit, and it's the model that they typically stop fitting. So they usually don't go any further. I encourage you to go further. So the third model, or the third type of model that we fit, is the means and covariances model. So the latent variable means are allowed to vary, but also the latent variable variances and covariances are allowed to vary. So this allows my classes to not only have different means, but have different amounts of between-person differences within each class. The last model is basically allowing all the parameters of the linear model to vary over classes. So we have the latent variable means, the latent variable covariances, and then the residual variances. So the residual variances are that last parameter allowed to vary over classes. And again, this is just with the linear growth model. So this is how people typically represent growth mixture models. They have their growth model as they would typically draw it, and then they have this latent class variable as a predictor of the intercept and slope. Now this is not at all as to how it's actually specified or how it's actually fit, but this is how it's often represented. And in this form, what they're essentially saying is that the mean of this latent variable and the mean of this latent variable is somewhat dependent on the class. So essentially they're fitting that second model where the means are dependent on the latent class variable. Now, I like to represent it this way because what we really have is we have a growth model for class 1, we have a growth model for class 2, and any parameter can be allowed to vary. So in this case, the only parameters that are superscripted are the alpha parameters. So this would tell me that this is a 2-class means model because the means of the latent variable are allowed to vary. And the class variable kind of puts you into one of these classes with a certain probability. Okay? Now I should say that I drew a diagram like this when I was in grad school and I submitted it to Psych Methods, and Bank Muten, who wrote Mplus, thoroughly trashed it. So if you want it published, you should probably put this diagram in. If you don't care if it's published, this one makes more sense to me. So this is about performing the search. So like I said, all the model parameters can be class specific, but I want you to use a systematic search procedure to try to figure out both how many classes there are, but also the location of their differences. And I kind of talked about those already, so let's move on. So what you have to do is when you specify one of these models, you're specifying what parameters are allowed to vary over groups, and you're also specifying how many groups you're expecting to find. So when you're writing the program, you're saying, I want 2 classes, and I'm allowing my 2 classes to differ in this respect. Okay? So what happens here is you end up fitting multiple models because you can fit a 2-class model where the groups are allowed to vary in their means. You can fit a 3-class model where groups are allowed to vary in their means, and you can keep on going. And if you think about all the different parameter combinations with classes, this is when people start to fit 200 models. It's like, oh, well, what if the residual variance is different? But what if the residual variance is the same and the intercept variance is different? What about the slopes, the mean slope? And you can just keep on going. And there's lots of different combinations that you can fit. And it becomes like an exhaustive search that just wastes a lot of time, in my opinion. So I try to be programmatic about the models I fit. So I start with the invariance model. It's the simplest model. There's one group. Then we move on where we have a 2-class model where just the means of the latent variables are allowed to vary. And then I would stay with that means model and move up to a 3-class model. If that fits better, go to a 4-class model. And I basically keep on going until things break down. Now, I find that things break down pretty quickly. 3 classes, sometimes 2 classes, things are breaking down. When people are publishing papers and they say they have 8 classes, I don't know what they're doing to find those 8 classes. They're restricting lots of things to be 0. Most likely, they're restricting the variances of lots of things to be 0. And if you restrict variances, you're basically saying everyone in the class is exactly the same. And that's never the case. Okay? So there should be variance within, the class. And so when people are finding lots of classes, oftentimes they're making very hard restrictions on their types of classes. So after I deal with the means models, I would then move to the means and variances model. And again, start with 2 classes and move up until things break down. Then go to the means, variances and covariances and residual variances. Move on up until things break down. So that's the search procedure that I use. And I think it's systematic. I don't spend weeks fitting these models. I spend a couple hours, and then I write my paper. So we have this weight data. It's organized in the wide form. The weight variables are weight 1 through weight 4 for the fall of kindergarten through the spring of first grade. And the time metric is simply going to be grade. So the data are pretty easy to set up because we just have 4 time points and we have discrete time points. So this is a 2-class means model. We start with the variable statement and we bring in all the variables that are in the data set. I have my missing variable indicator. I have my use variable command, which are just the variables I want to use for this analysis, which are my weight variables. And then I have a classes statement, which says how many classes am I going to fit with this model. So this is a 2-class model. So I have classes equals C with parentheses and then 2. Okay? This C becomes very important because that's what I'm actually going to use when I specify my classes. So the C is essentially the latent class variable. The analysis type is a mixture model. Then in the model statement, I specify my model. And again, here I want you to specify the model as complete as possible. Because again, Mplus has defaults. And it's going to go to those defaults if you don't specify things. So I have percent overall percent, eta 1 by weight 1 through weight 4, fixed weights of 1, so that's my intercept. Eta 2 by weight 1 at 0, weight 2 at 0.5, weight 3 at 1, weight 4 at 1.5. That's my linear growth model scaled in terms of years. And now what I do for all my estimated parameters, I label all of my estimated parameters. So eta 1, the variance of eta 1 is psi 1,1. Eta 2 is psi 2,2. Eta 1 with eta 2 is psi 2,1. Eta 1 and eta 2 are in brackets. Those are the means. Since these are the parameters that are going to vary over classes, I don't need to label them. And it's in certain versions of Mplus, if you label them, it will give you an error message. So it depends on which version of Mplus you're using. And then I have weight 1 through weight 4, which are the residual variances, and I label them theta because, again, I'm constraining them to be equal across time. In the 2 statements down here are group-specific statements. Right? So I say percent C #1%. This C variable is the same as the C variable up here. So if I use C up here, I use C down here. So this is for class 1. And in brackets, I put eta 1 star 30 and eta 2 star 3. Okay? These are starting values for class 1. And then I have class 2, so percent C #2%. In brackets, I have eta 1 star 60 and eta 2 star 8. Again, starting values for those, the means of the intercept and slope for the two groups. I find it useful to help Mplus and give starting values. And I choose starting values that are kind of on the extremes of the distribution. So if you were to go back to the weight data, you would see that 30 pounds is pretty light for a second grader, and 80 pounds is kind of on the upper end for a second grader. So I'm starting my two classes in different places. If you start them in the same place, it's hard for them to separate. So starting them in different places can be beneficial. If I want to fit a model with means, variances, and covariances allowed to vary, I just need to change my class-specific model statements. So now I just put the variances here and their covariance. So eta 1, eta 2, eta 1 with eta 2. And I put that in both of my class statements. Typically, you don't have to provide starting values for the variances and covariances. The default starting values in Mplus work fine. Starting values for the means are more important. If you want to allow the residual variances to vary, you then put those statements in here, weight 1 through weight 4. I'm calling this theta 1. And then down here, weight 1 through weight 4, I'm calling this theta 2. So this will constrain them to be equal across time, but allow them to be different between my classes. So here's the beginning of the output for the two-class means model. The first part of the output gives me some fit information. It gives me the number of free parameters. I have 9 free parameters. So in a growth model, I have 6 free parameters. I have the means of the intercept and slope, the variance of the intercept and slope, their covariance, and the residual. Okay, with a two-class means model, I have 2 more means. I have the means of class 2, mean of the intercept, and mean of the slope for class 2. But I have 9 parameters. My last parameter is the mean of the latent class variable. Okay, that's the variable that's going to divide my sample up. It's going to tell me how many people are in each class. So those are my 9 parameters. I have a likelihood value right here, and then I have information criteria. And again, people typically will look at the BIC to let them know if this model is a better reflection of the data or not. So the BIC is an important statistic to track across your models. The next part of the output tells you information about how many people are in each class. So the first part says final class counts and probabilities for the latent classes based on the estimated model. So there's an estimated mean for the latent class variable. Based on that estimated mean, you can figure out how many people belong in each class. If they do that, there's 990.6 people in class 1 and 92.4 people in class 2. Okay? I would encourage you to put those numbers in because those are your best estimates. Okay? The next part says the final class counts and probabilities for the latent class patterns based on estimated posterior probabilities. So with this model, you can estimate the probability of being in class 1, the probability of being in class 2. If you add up all the probabilities of being in class 1, you get 990.6. If you add up all the probabilities of being in class 2, you get 92.4. Okay? This next part here assigns people to a class and then counts up how many people are in each class. So if you're 75% likely to be in class 1, this part says you're in class 1. Okay? And so now we have 994 people and 89 people. This is what people typically report, but I would encourage you to report the top one because it's the most accurate one. And the thing is, if your model, excuse me, if your model fits well, represents your data well, these two numbers will be very similar. As you see, these numbers here are very similar. Okay? If your model doesn't fit well, these two numbers start to become very different from one another. And that's a problem. And that's something that you should be aware of. The next thing that's reported is the entropy. The entropy is a measure of classification quality. It ranges between 0 and 1, with higher numbers indicating that it's easy to separate the people into groups. So a 0.94 tells me it's pretty easy to separate people into groups. There's really no lower bound on this value, but of course people like to put lower bounds on it, and people have put lower bounds at 0.8. But again, completely arbitrary. The next part says average latent class probabilities for most likely latent class membership by latent class, which is a whole lot to say. If we think people are in class 1, we're 99% sure they're in class 1 on average. If people are in class 2, if we're putting people in class 2, we're confident about 92% of the time. Okay, so it's about our confidence and how easy it is to classify people. After all this information, they finally give you your parameters. Okay, I think they should probably give you your parameters up front, because people start to look at fit and they start to get all happy, and then they look at the parameters and they say, what the hell's going on? But our parameters in this case are pretty straightforward. Remember, the only parameters that are allowed to vary over classes are the means. So those are the only parameters that are going to be different. Important to check though, to make sure your variances are not negative. A lot of times you'll get variances that are negative, covariances that are greater than 1. You'll get lots of issues with these models, okay? And those are kind of all features that say, stop. Stop this right now, don't do this. But if we look at the means, class 1 has a weight on average of 44 in the fall of kindergarten, and they're increasing about 6 pounds per year, okay? Class 2, which only has about 10% of my sample, has a weight of 64 pounds in the fall of kindergarten and increases 15 pounds per year, okay? So these seem to be somewhat pretty different trajectories. We have a group, 90% of our sample, that's about 45 pounds and increases 6 pounds per year, which, we can call it normative because it's 90% of our sample. And then we have a class here that might be somewhat overweight. Again, 10% of our sample. This last parameter here is the mean of that latent class variable. Okay, this 2.372. Okay, that is in a logit metric. Okay, so you can transform it back to the probabilities. Okay, if you do that, you'll get the probabilities that were reported up front, because that's the parameter that those probabilities are based upon. There's additional output that people always like to report. It's in the Tech 11 output from Mplus. The first one is the Low-Mendel-Rubin likelihood ratio test. It gives us 2 p-values. They're slightly adjusted from one another. They're typically very, very much the same. What these p-values are trying to compare, they're trying to compare the model that you fit to a model with one less class. If the probability value is low, then it means that the model that you fit fits better than a model with one less class. Okay, so if these values are low, it gives you a sense that your model fits better than a simpler model. Okay, so this tells me that these 2 classes seem to fit better than a 1-class model. The next thing is the bootstrap likelihood ratio test, which is another pseudo likelihood ratio test. It gives us another p-value. Again, it's a p-value for comparing the model that you fit to a model with one less class. Now, there are some papers that have recommended that the bootstrap likelihood ratio test is a good indicator of how many classes you have. When I fit models, I get 2 values for the bootstrap likelihood ratio test, 0.00000 and 1.0000. So it either tells me it's much better or it's the same. So I'm not so confident about the bootstrap likelihood ratio test. I tend to like this Low-Mendel-Rubin adjusted likelihood ratio test. All right, so what we do is we fit all these models. So we fit the 1-class model, 2, 3, and 4-class means models, 2 and 3-class means and covariances models, 2 and 3-class means, covariances, and residual models. And I stopped fitting models once I started to run into problems. So things stopped converging. So you should know that this 4-class model either had a parameter estimate that's out of bounds or it didn't converge. This 3-class model, same thing. This 3-class model, same thing. So I'm fitting models until they break down. And you see they break down pretty soon. Trying to figure out which model to select is probably the biggest issue. And people argue about it all the time. People do lots of simulation studies. And every time they do a simulation study, they find a different answer, which makes you really confident that you can trust them. But basically, I mean, they come up with a simulated population, and so much is based on the simulated population. So, they always say something else. So, likelihood ratio test, BIC, sample size adjusted BIC, bootstrap likelihood ratio test. I don't say use one, I say use all of them. All right? don't use one statistic. Anytime someone says, oh, this person said the BIC is the best thing, and so I use the BIC, I say, well, nothing else agreed with you. You know, so report all of them and then justify your choice. Because I don't want you to, it's almost like I don't want you to convince me that you're right. I want to understand why you chose the model that you chose. I want to say, okay, maybe I don't agree with you, but I get it. You know, I don't expect everyone to agree with me most of the time. But, you know, I want to understand where you're coming from when you make a decision. So consider all the available fit information. Use your mind about what might be reasonable, what might replicate in a new study. Use theory to help you guide this. If there have been other studies similar to yours, use their results to try to support your results. Okay, these are all important things to think about. And of course, most important is to think about things that might replicate. Who wants to do a study where they have the only finding? You know, you want a study where people can replicate. People tend to find similar things. If a lot of people tend to find similar things, you might say, well, actually there might be groups here. It's not just a fluke with your data. There might actually be some groups here. So here's my table. I have my one class model, my means models, my means and covariances models, and my means, covariances, and residual models. So I have all my information. If we look at the BIC, to go from the one class model to basically any mixture model, you see large decreases. So that kind of tells me that, you know, it seems like there might be some usefulness of having these latent class models. My means models all have very high entropy. My statistics here are very good. It tells me that this two-class model fits better than this one-class model. This three-class model, you see some of these start to bump up. So this is telling me the three classes here might not be any different from two classes here. So I would try to be conservative, so I would go two classes here. But of course we have these other models. The two-class model here didn't converge properly, so that one's gone. This two-class model here is somewhat interesting. The BIC is a good bit lower for this model. It's about 1,000 points lower, or 1,500 points lower. The entropy is a little concerning. It's 0.81. It's not as high as the other ones. My statistics here are good. So I'm really left with this choice of this two-class model and this two-class model. Now the thing is, I can't really compare them on any other statistic beside the BIC. But I don't want to base everything on the BIC. I have a pretty good sample size here. BIC is heavily influenced by sample size. So, you know, a little bit of improvement in fit can lead to a big change in the BIC. So I need to really think about this carefully. So this is kind of the approach that I tend to take when looking at fit. You know, first examine model convergence. If things don't converge, toss them out. Don't need to deal with them. Look at the BIC. If the BIC is not going down, there's not anything to look at. If the BIC goes up, you know, don't even worry about it. When I fit models, I never see the BIC really stop decreasing. It keeps on going down. And so that tells me just, you know, that some other criteria is going to tell me to stop first. After the BIC, look at the likelihood ratio test. Again, these likelihood ratio tests are the ones that I prefer. The entropy, you know, if your model has poor entropy, I don't think about it. The BIC can drop all it's want. If I can't figure out who to put in what class, I don't need this model, okay? So obviously models with greater entropy are preferred. Examine the interpretation of model parameters. Obviously very important from a theoretical perspective to make sure things are reasonable. And then finally, just reason with your results. So one thing you can do with the BIC is you can plot it, and you can kind of maybe try to treat it like a scree plot, trying to look for an elbow. So you see that we get a big drop in the BIC when we move to two classes for the different models. When we go to three classes, you see it really flatten out. So even though the BIC continues to drop, it's not dropping that much. So this would really tell me, again, another indication that three classes are just too much for these data. Again, there's no right answer. There's no right decision when you're making this. Try to justify yourself with the information that you're using. What I decided with this example, and I decided it for two reasons. So the first thing we decided was that we decided upon the two-class means, covariances, and residual models, that last model. The entropy was 0.81. It's a little low, a little concerning. The BIC did drop a good bit. My sample size is pretty decent though, so I'm not so surprised that the BIC dropped. But part of the reason I selected this was because I wanted to encourage people to look for models that aren't typical. Most people will just look at means. It's important to look at means, variances, and covariances. And this model is kind of a nice picture of that. So you should know that I kind of chose it for a teaching perspective. These are the model parameters, which I find incredibly interesting. So we have 824.28 people in class 1, 258.72 in class 2. These are the means of their intercept and slope, 43 and 5, 54 and 10. So this class is a little bit heavier at the onset, gains a little bit more weight on average. But then look at these variances differences. The variance of the intercept here is 24.6, and here it's 134.8. So there's a lot more between person variability in this second class, especially in the slope. Again, a lot more between person variability, and also in the residual. So these people are bouncing around a lot. They differ a lot from one another. They tend to gain more weight on average, but they're really jumping around a lot. They're not consistently gaining weight. They're bouncing around. And another important thing to do from these results is to make plots. And typically what people do is they plot the means. Okay, and they say, look, one class is up here, one class is up here, look, they're different, right? But they don't think about the variance, okay, and the between person differences. This is class 1. 95% of my class 1 is right here. It's almost like a subsample of class 2, which is right here. So my two classes completely overlap with one another. Okay, they completely overlap. But this is where, 80 to 90% of my people are right in here, very consistent. But I have this other group that's inconsistent, a lot of differences between these people. They're not one type of people. There are lots of different type of people, but one thing that's consistent is that they jump around a lot. And on average, they tend to gain more weight, which I think is a kind of an interesting phenomena. All right, so with approaches, again, look at the literature, think about what might be reasonable, be cautious. Don't, run and fit these models and then celebrate. Be cautious, make sure things converged. Think about a systematic approach to fitting models, because if you're searching for, any parameter that's different, you're going to find it, and it's probably not going to be, replicable in a new sample. So again, use a systematic approach, an approach that you can try to justify. You should know that solutions are notoriously unstable. Using multiple sets of starting values is beneficial. Mplus now does this by default, unless you provide parameters. Look at the distributions of your outcomes. Again, we're just trying to model non-normality, but with growth mixture models, it's a certain type of non-normality and how the non-normality changes across time. Also, if your variable is like polynomous and you're treating it as normal, you're probably going to find mixtures, because polynomous data just are typically non-normal. So make sure you think about the outcome and how it's distributed in your data set. If you have polynomous data, you should use a polynomous model for it, instead of trying to figure out that my distribution's terrible, well, I'll find mixtures. So really think about the outcome and how it's scaled. You should also think about different types of trajectories, whether or not different types of trajectories can actually account for the mixtures. There's a paper that we wrote where we had this really nice clear separation of two classes. One went up and down, the other one went up and stayed. After that paper, I said, well, let's fit a model where I have two phases of development, on a first phase and a second phase. I do that. That model fits better than the mixture models. I try to find mixtures upon it. I find nothing, because I'm accounting for the differences I found in a mixture with another growth parameter. Instead of one thing going over time, I had two things. One thing here and one thing here. So it's very much dependent upon the growth model you fit. And maybe you found them because you just didn't try hard enough. You just didn't try hard enough with your growth model. Okay, so you were too satisfied with your growth model, and so you needed mixtures to kind of fix it. If you're including covariates, covariates can impact your classification, and this has been a big issue. You have a nice mixture distribution, you add a bunch of covariates, your classes are all different. And you're like, why? The problem is your covariates might be non-normal too. And if they're non-normal, they're going to infiltrate your longitudinal data that you believe are non-normal. There are now different ways to include covariates. There's an auxiliary command in Mplus that is now the preferred way of entering covariates. In this sense, the covariates, they don't impact they don't impact the classification, and they simply relate the classification to the covariates. So it's exactly what you want. The classes remain what you found without covariates, and the covariates are now being associated with the classification, which is exactly what you want. So this is now available. It became available about 2 years ago. So that is all I have, and it's 5:01.
Thank you so much, Kevin.
Thanks, everyone.
So I just wanted to remind everybody that March 13th we'll have the SRCD poster symposium here in this room. So, and if you haven't already contacted Jason, I think he's going to be sending out an email to everybody shortly, because we have lots of people who have posters. If you have a paper, you can also submit it to Jason in a poster format, so you can practice your paper presentation as well. And so we look forward to seeing all of you there. And thanks again, Kevin. It was
No
great.
problem.
It was really great. Thank you.
And if you have questions, feel free to email me. I'm happy to answer questions. So just